2 days.
Oh, okay, good.
But yeah, so there are 3 sets of
Pass this one around.
All right.
Then this one can use it.
Yeah.
Whenever you want
also,
to,
also
even if you want to speak to the Zoom call, you can use it.
Okay.
Yeah.
Right.
Just to maybe to alert 2 minutes left, 1 minute left.
Yes. For the
you're gonna sit there.
When I'm the chair, I'll be sitting there. But if not, I'll be sitting here.
Okay.
I'll move around. Also more questions. Right. But for the people on.
One, two, three, four, five, six, 1, 2, yeah, 1. 2, 1, 2, 2. 1, 2, 2. 1, 2, 2. 1, 2. 1, 2. 1, 2, 2, 2. 1, 2, 2. 1, 2.
This is the price. I'm just checking my slides.
Can I try this one? Can I press? Just want to see if. These two. Okay. I have some laser.
The example is like, you see one like this.
About this
Yeah,
distance.
yeah. So if I check like this, as I put you can see that it's making a funny noise. But if I stand close, then I'll just push it up. That's it.
So about here, this distance is enough. You can hear me well, right? Okay. Okay, good. Are you speaking? Tomorrow, okay. Check, 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 check.
Okay.
Hello, hello.
I think that's can you check?
You mean closer? Blah, 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 blah. Okay. Okay. All right. Yeah, thanks. Good to know.
Yeah, if you this one, if you use this one, ask it yeah. If you want to move, you can just put the two.
Must be in the right room.
It might seem crazy what I'm about to say. Sunshine, she's here, you can take a break. Hot air balloon that could go to space. With the air, like I don't care, baby, by the way. Because I'm happy. Clap along if you feel like a room without a roof. happy. Clap along if you feel like happiness is the truth. Because I'm happy. Clap along if you know what happiness is to you. Because I'm happy. Clap along if you feel like that's what you want to do. Here come bad news, talking this and that. Give me all you got, don't hold it back. Well, I should probably warn you, I'll be just fine. No offense to you, don't waste your time. Here's why. Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you feel like happiness is the truth. Because I'm happy. Clap along if you know what happiness is to you. Because I'm happy. Clap along if you feel like that's what you want to do. Bring me down, can't none bring me down. The love is too high. Bring me down, can't none bring me down. I said, bring me down, can't none bring me down. The love is too high. Bring me down, can't none bring me down. I said, cause I'm happy. Clap along if you feel like a room without a roof. Cause I'm happy. Clap along if you feel like happiness is the truth. Because
One,
I'm
two,
happy.
cool.
Clap
Hey,
along
one, two.
if you know what
Testing again.
happiness
One,
is
two.
to you.
One, one, two. Hey,
Clap
hey,
along
hey.
if
One,
you
two.
feel like that's what you want to do. Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you feel like happiness is the truth. Because I'm happy. Clap along if you know what happiness is to you. Because I'm happy. Clap along if you feel like that's what you want to do. Bring me down, can't none bring me down. The love is too high. Bring me down, can't none bring me down. I said, cause I'm happy. Clap along if you feel like a room without a roof. Cause I'm happy. Clap along if you feel like happiness is the truth. Because I'm happy. Clap along if you know what happiness is to you. Hey, hey. Clap along if you feel like that's what you want to do. Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you feel like happiness is the truth.
Hello, people online. Can you hear us well?
Yes, I can hear you.
right, I think it's time. Welcome everyone to Focus Meeting 4, Supernovae and Massive Stars. Really happy to see you here. And the idea of this meeting is to bridge the two communities together, Supernovae and Massive Stars, to get some discussion and try to understand some of the most interesting things that we have. And today we'll start with the Supernova talks, and tomorrow we'll have the Massive Star talks. But in between, of course, let's try to have as much discussion as possible. And yes, I'm Hani Kunchuriakti, the SOC chair of this meeting. Unfortunately, I'm alone here, and some of the SOCs are they're online. But anyway, we'll start the meeting with a talk from Daichi Ramatsu on a general review on supernovae populations. Thank you, and I'm looking forward for a great meeting.
All right, thanks for the introduction, and thanks for the organizers for having me. This is my first time in Africa and IAU, so I really appreciate these opportunities. So my task today here is to give you an overview of core collapse and superluminous supernovae, only in 90 minutes, so it's going to be challenging, but I'm going to try. So let's see. So let's start with the stellar evolution. So this is a stellar evolution in a nutshell, but today I think this whole meeting is focusing on like massive star evolution, where we are talking about like about 10 solar masses or so. At the end of their evolution, they form an iron core, and then they can no longer fuse any heavier elements, so they lose the pressure support, and then they collapse. And then that's what we see as the core collapse supernovae that could leave either neutron star or black hole, depending on the initial mass. And then, these have implications to overarching questions like stellar evolution, explosion physics, nuclear synthesis, chemical evolution, and then also the remnant population. So this is why we study supernovae. And for supernova classification, what you want to keep in mind is that we use type 1 for hydrogen poor and type 2 for hydrogen rich. And then here I show some nuclear supernova is coming called type 1A, is coming from white dwarf explosions, which I don't talk much about it in this meeting. And then today we focus on the core collapse supernovae, where you see type 2 supernovae, in which you see hydrogen emission lines. And then for type 1B, where you see helium. And then for type 1C, you don't see hydrogen or helium. And then for type 1C blood line, you see a really blood line. So this indicates high velocity. And then these are the class that is usually associated with the wrong GRB. And then if you look at these core collapse supernovae, so these are the explosion of massive stars. And then canonical explosion energy is roughly 10 to 51 arcs with an equal mass of 0.1 solar masses. And then these are the progenitor structures. So starting from type 2, where you have hydrogen rich, and then if you strip hydrogen rich envelope, you left with type 1b, and then if you strip even more, you end up with type 1c. So this is, so the final state of the progenitor reflects what we see in the supernova explosion. So this is how we connect the stellar evolution to supernovae. And then let's move on to hydrogen rich type 2 supernovae. So their progenitors are red supergiants. And then this is confirmed by the direct progenitor identifications in the pre-explosion images. And then what we see in the supernova observations in spectra is that we see a p-signal profile of hydrogen. And then in the light curve, we see roughly 100-day plateau of the luminosity. And then their emission mechanism is that they're emitting, so it's coming from the shock deposit envelope, and then as the envelope expands, it cools down. And then they form a photosphere at the recombination temperature of hydrogen, which is roughly 6,000 Kelvin. And then as it cools down, this recombination front moves inward in mass coordinates, but at the same time, they're expanding in the physical coordinates. So this roughly results in a constant physical radius. And then if you fix the temperature and then the radius by black body argument, you get the plateau in the light curve. And there is a scaling for these type 2 supernovae where you can scale the luminosity and then the plateau duration with the explosion energies, ejector mass, and then the progenitor radius. And then once the photosphere reaches inside of the hydrogen-rich envelope, the opacity drops, and then now it's purely powered by the radioactive decay of cobalt. And then this is what we call as a radioactive tail. And in this phase, the supernova ejecta becomes optically thin, so you can actually start to see the core elements and then what's synthesized in the explosion itself. So this is a really strong diagnostic on the exposure mechanisms, depending on what lines you see in the nebula phase. And then there's a light curve subtypes of type 2 supernovae. There are type 2 supernovae, where P stands for plateau that I just mentioned. And then there's a type 2L, which shows a linear decline. And then type 2B, that shows sometimes like double peak light curve structure. And then initially these are thought to be distinct classes, but now we have more supernovae. And then I think what we are seeing is a continuous distribution of these light curve properties. And let's look at the light curve. So this is also supported by the theory as well. So if you run a numerical light curve modeling, depending on the hydrogen-rich envelope masses of the progenitors, you start with type 2 with the most massive hydrogen-rich envelope. And then if you strip even more, you get type 2L, and you keep stripping. There's a rare class of so-called short plateau. And then if you strip even more, you get type 2B like light curves. So these are characterized by the double peak light curves. And then now, if you strip even more, you become hydrogen poor. So these are called type 1 supernovae. And then sometimes people refer these class as stripped envelope supernovae because the envelope is stripped. And then in here, I'm showing an example of type 2B light curves. And in this case, it's color-coded by the Nico mass. So what you see in the initial phase is the shock cooling, because it still has some hydrogen-rich envelope, puffy hydrogen envelope of order of like 100 solar radii or so. And then in the later phase, it is now powered by nickel and cobalt decay. And then since I'm plotting the different nickel masses, you only see the differences in this second peak. And then because of this extended envelope structure, these are sometimes called E2B, where E stands for extended. And then these properties are consistent with yellow supergiants. And then this is also confirmed in some direct progenitor identifications in the pre-exposure images. And then if you strip even more, you no longer have hydrogen-rich envelope. So you end up with a single peak event where this peak is powered by the radioactive decay. So you have this type 2B, which is a spectral subtype transitioning from type 2 to 1B. So it starts from hydrogen-rich and then becomes hydrogen-poor. And then type 1B, you start with hydrogen-poor. It stays at hydrogen-poor, but helium-rich. And then 1C is both hydrogen and helium-poor. And then there is below line 1C where you say high velocity. So here, it's not. And then if this is purely powered by the radioactive decay from the diffusion argument, you can get the scaling for the rise time and then the peak with the opacity, ejecta mass, and kinetic energy. And then the peak is almost like controlled by the nickel mass. So in general, 1BC have really similar light curves, and then 1CBL is usually brighter than type 1B and 1C. So this is likely because of their high explosion energies and high nickel mass. But we can have dependence on the helium abundance than hydrogen-rich envelopes. So to find the characteristic, masses for the helium-rich envelope, you have to rely on the spectral modeling. And then this is what's shown here, where it's plotted as there are some models for 2B transitional cases and type 1B. And then you ask the question where you see the disappearance of the hydrogen line in the spectra. And then this transition corresponds to roughly 0.03 masses, solar masses of hydrogen-rich envelope mass. And then this corresponds to type 1B to 1C. And then you ask the same question where you see the disappearance of this helium line. And then this 1BC transition corresponds to 0.06 solar masses. And then if you look at their ejecta mass distribution, surprisingly, they have really small ejecta masses. So, from these transitional masses, you might expect they are Wolf-Rayet stars, but maybe in many cases, these are low mass helium or carbon stars where the stripping happens in a binary system. And then I'm jumping on to the superluminous supernovae. So again, they are classified by the presence of hydrogen or lack of. So hydrogen poor stands for SLSN1, and then hydrogen rich corresponds to SLSN2. And then they identify their brightness, as the name suggests. So compared to the typical core collapse supernovae that I've shown, they are roughly 10 to 100 times brighter. And then, but now these days, it's more like a spectral class. So if you look at the spectrum of SLSN1, you see a really blue continuum, and then the characteristic O2 complex. And then this corresponds to a really high photospheric temperature of roughly about 15,000 Kelvin. And then if you look at the spectra of SLSN2, most of them are characterized by the narrow emission lines, but some of them, like rare events, show broad lines. And then, so what's the emission mechanism? So for type 1 superluminous supernovae, so if you assume a radioactive part, and then you get this scaling again, and then if you plot this as a function of peak luminosity and then the light curve duration, the unshaded region is where you have the neutron mass greater than the ejector mass. So this is unphysical, but many of the superluminous type 1 actually lies in that parameter space. So radioactive decay cannot be the sole power source for these type 1 superluminous supernovae. And then the promising power source for these type 1 superluminous supernovae is that they're powered by the magnetar spin down. So they leave a magnetar after the explosion, and then that's giving an extra energy or the boost in the luminosity. And then you can get the, spin down energy and then the time scale, depending on the period and then the magnetic field of the magnetars. And then by, again, diffusion argument, you can get this scaling for the luminosity of the peak. And then now you plot the same figure again. And then now, within a reasonable magnetar parameter space, you can reproduce these, like a peak and then the duration of these type 1 superluminous supernovae. And then for type 2 superluminous supernovae, many of them, again, show narrow emission lines. So these are likely powered by the interaction between the supernova ejector and then the CSM. The shock interface happens, forms between these fast-moving supernova ejector and slow-moving CSM, and then that's where the photosphere forms, and that results in the narrow emission lines you see in the spectra. And however, these emission mechanisms may not be the sole power source for the broad line, so this still remains to be a question. Maybe they are more like type 1 with a small amount of hydrogen-rich envelope mass, so this is a remaining question in the field. And so I'm just going to move on to some recent events, given the limited time, of core collapse and superluminous supernovae. So one is this 2023 IXF. So this is a type 2 supernova that happened last year at 7 megaparsec. And amazingly, this was discovered by an amateur astronomer in Japan called Koichi Itagaki. And my personal story is that I got an email from him on the Friday evening in the US time that he found this supernova. I was drinking at the bar, but for some reason, I was checking my emails, and then the bar had Wi-Fi. So I started triggering observations using the Last Converse Observatory network of telescopes, and then also the space telescope. And then, so this is his last known detection, which was 2 days before the explosion. And then this is his discovery image. And then to put in the context, this is the location of 23 IXF in the spiral galaxy of M101. And then there's a progenitor candidate at the pre-explosion site. And I think Monica is going to talk about this. So if you look at the spectra, traditionally, we can only get a spectrum 5 days after the explosion or so, where you see blue continuum, because you are seeing the cooling emission. But these days, with the recent advancements in the transient surveys and contribution from amateur astronomers, we can get to see spectra right after the explosion from 1 to, starting from a day after the explosion or so, where you see these strong narrow emission lines, which we think is coming from the fresh ionized lines of the CSM that is powered by the shock breaker radiation from the supernova. And then what's interesting for this particular supernova is that we see a transition of the ionization state from C3 to C4. So it started with strong C3 lines, and then it transitioned to strong C4 lines. So this likely indicates the rise in the temperature because the ionization state is increasing. And then these flash features disappear when the supernova ejecta completely overruns the CSM. So from this, you can get, Lafferty like radial extent from the time scale of the flash features. And then this CSM has a really compact radius of 7 times 10 to 14 centimeters or 10,000 solar radii. And then if you look at the light curves, given the amateur contributions, we started observing of the supernova from -10 in absolute magnitude, and then it rose to -18. So we saw a rise of 8 magnitudes in 5 days. So this is a pretty amazing data set. And then you see a plateau. So it's classical type 2 light curves. And what's interesting here is that if you look at the UV evolution, it becomes bluer in the initial few days and then becomes redder. This is unexpected in a regular type 2. And then if you look at details, this color evolution started from 2 hours. The first color observations it happened only 2 hours after the explosion. And then it showed this dip that the color was becoming bluer and then became redder. So this likely also indicates there is a certain amount of CSM where the photosphere initially forms in the optically thick CSM. And then as the supernova shock front propagates through, it becomes bluer and bluer because you get more radiation from the supernova component. And then from this timing argument, you can also get an estimate. Again, you get a really compact CSM radius. And based on these, you can perform some light curve modelings. So what's plotted here is the optical luminosity as a function of time. And then these models are color-coded by the explosion energies of the models. And then whatever explosion energy you use, reasonable explosion energy from 1 to 24, 2 times 10 to 51 arcs, you cannot reproduce the really bright peak. So here again, you need some CSM. So if within the constraint of the observations, you can so it has to happen in the 2 to 1 years before the explosions. And then you need to have really extreme mass loss. If you assume a wind-like mass loss of 0.3 to 1 solar masses per year, that is plotted as a yellow line here, that can roughly reproduce the light curve peak. And then if you assume a different mass loss mechanisms like eruptive mass loss, and then here it's the light curves are color-coded by the injected energy, which is a fraction of the energy injection to the binding energy of the envelope. So as this number goes up, you get more mass loss. But for the best fit, we get this eruptive mass loss happened roughly a year before explosion, and then it lost 0.3 to 1 solar masses of CSM. So these are good fits. So the complicated picture is because of, a lot of observations we get arises for 23 IXF, but perhaps this might be a common picture for all supernovae. If you could get all of these kind of observations in any supernovae, because there's no reason to believe that this is a unique supernova. So from the Progenitor, observations, I think Monica is going to talk about, but these are the constraints of the mass loss rate from the dust extinction, and then the radius of this dust shell. And then from what we talked about in this presentation, the CSM velocity is roughly 50 to 100 kilometers per second. And then there is a really dense confined shell of CSM. And then there might be a density transition that is correspond to maybe that might be the explanation for why we get different estimates from the light curve and then the spectrum. And then there is no outburst in the archival images. And then from this, you can constrain the CSM mass from eruptive-like mass loss, which is upper limit is 0.3 solar masses. And then as the shock propagates through this dense confined shell, it starts to interact with the underlying CSM, which is coming from the progenitor wind. And then there's an X-ray detection that is consistent with what we got from the progenitor identifications. But for some reason, there was no radio millimeter detections. So this is in conflict with the X-ray observations. If the mass loss estimates from the X-ray observation is correct, we should have detected something in radio, but we didn't. So this is a remaining question. And so to put this in the context of massive star evolution, what's plotted here is the mass loss rate on y-axis and then expansion speed. So this is the speed of the CSM, and then known massive star populations, right? Red supergiant, something like a Betelgeuse, and then some really extreme case like a luminous variable, giant eruptions that we see in luminous variable. Example is an Eta Carina here. So from the progenitor observations, IXF is somewhere here. So that is consistent with what we expect for this kind of massive star. But then from the supernova observations, from this really confined dense shell, like mass loss rate and then the speed is somewhere here. So these days, like recently, we identified these huge discrepancies between the mass loss estimates, especially in the last few decades, from stellar evolution theory and then the supernova observations. So what is causing this enhanced mass loss in the final moments of massive star evolution? Could it be an internal gravity waves, excited by some shell burning, or maybe there's binary interaction? So we're gonna hear more about this in tomorrow's sessions. I'm really excited to hear. And then recently, also similar interaction signatures have observed in hydrogen poor envelope supernovae. So these new classes are called type 1Bn, 1B with the interaction lines N, and then 1Cn. And then there are also 1B and 1C with late time interaction, where they start interacting with the circumstellar medium like a year after explosion. So they have this detached CSM shell. And then if you think about it, the density of the CSM scale as the mass loss rate divided by CSM velocity. So for these compact massive progenitors that you'd expect for 1B and 1C, you'd expect a low circumstellar medium density. But to get these signatures, a big question here is what's the CSM density structure? And then we're gonna hear more about this in today's session. So yeah, stay tuned. So I think this is it for my talk. Thank you so much.
Thank you, Daiji. Wonderful talk. Can I invite questions? Mr.
Yeah, thanks for the overview. I have a question. How come an amateur astronomer is more efficient than all those all-sky surveys that we have nowadays?
Yeah, so for this particular course, I said Koichi Takaki is an amateur, but in practice, he's professional. It's just because he's not getting paid by what he's doing. That's why I call he's amateur, but he has a network of telescopes in Japan owned by just him. So he has 3 sites in Japan with 6 telescopes, 0.5 to 50 centimeter telescopes. And it's robotically controlled. and then I think his location is also his strength in that, there's no big transient survey running in Asia. So that's a gap in the large transient survey at the moment. Yeah.
Yeah, thank you very much. Really excellent overview. You mentioned this late mass loss a few slides back for the type 2 supernovae, and you said that this is mainly, this may be inherent to all the supernovae. Does that apply only to type 2 or also to the stripped envelope, would you say?
Yeah, so that's a good question. I don't know, to be honest, but I think the recent observations, I think Anjasha is gonna talk about more in afternoon session, but we are identifying this class called 1BN and 1CN. So they show strong signs of CSM interaction. So it looks like they might also have this enhanced mass loss, but the time scale is not well constrained. So it might be happening in the final decades or so, but given the high velocity that you'd expect for these massive and compact objects, I think it's happening in the final year or decade. So this is and then this is the temporal regime you can only study with the supernova, because in the galactic stars, you can never get to this final stage of these massive stars. So this is a really exciting era. And I think this is the main theme of this session.
Okay, I would like to ask to online participants if there is any question No, one more question for Daichi from.
Thanks for the great talk. Are there any polarimetry studies of 2023 IXF? Is there any indication of asymmetry in the distribution of the CSM or?
That's a great question. And the answer is yes. Sorry, I couldn't talk about this, but I put it here. So there's a polarimetry observations, both spec and FOT. And then, as you know, there's a detection. So there is a 1%, like, you know, polarization. So that corresponds to more like a football shape, like, you know, structure. So maybe the CSM, and then the polarization like switched when the CSM dominated, you know, from the CSM dominated phase to supernova dominated phase. So it started with a, you know, football like shape. So that's roughly corresponds to like, you know, what the CSM looked like. And then when it becomes supernova phase, the polarization angle switched. So there might be misalignment between the, you know, supernova ejecta and then the CSM distribution. So that's a really interesting topic for this one.
Okay, let's move on and thank Daichi again.
Thank you
so much.
Also, I have some milk cookies from Japan. So if you want to get it, just talk to me in the break.
Okay, next presentation is by Monica Soraisam. Are you here? The slide, please. Yes, please, you have 9 + 2 minutes.
Okay, hello everyone. I'm Monica Soraisam. I'm an associate scientist at NSF NOAA Lab Gemini Observatory Program. Daichi has given a very nice overview of the 2023 IXF supernova. So in this talk, I'll summarize our main results on the progenitor of the supernova, which is like the closest in a decade or so, and has given us an unprecedented view into the explosion of massive stars. Okay, so as Daichi mentioned, the supernova went off in this famous pinwheel galaxy M101 at a distance of roughly 6.8 megaparsec. It was discovered by the famous amateur astronomer Itagaki on May 19, 2023. This was actually a question from an audience here. This is a nice light curve of the supernova taken by ZTF. And the cutout images there are from the first detection by ZTF. We were actually alerted by this software system called the Antares Event Broker at that point, which was roughly 10 hours prior to Itagaki's discovery. So notification was in our inbox, but you know, we missed it. All right, so if you go to ADS, you find more than 50 publications on this single supernova, which I think is a testament to the interest and excitement generated by this supernova. So thanks to the proximity of the host galaxy, which has been frequently observed in by both space and ground-based facilities in the past, we now have a clear detection of a source, a red supergiant star, at the location of the supernova in these archival data. Okay, so on the far right is the HST optical image. In the middle are the ground-based near-IR data of the supernova, and on the left are the mid-IR data from Spitzer. Okay. In this recent work from our group, led by Skylar van Dijk, we presented a sweeping analysis of the whole ensemble of archival data across the infrared and optical wavelengths. So the resulting SED of the progenitor is shown here. And on the left-hand panel, these solid lines are fits to the SED model, to the SED of the progenitor. They are based on the Grimes model. And this dashed line, this is the Phoenix stellar atmosphere model for a temperature of around 3000 Kelvin. And the main takeaway here is the enormous dust obscuration in the progenitor star. So whereby the optical emission has been highly suppressed and reprocessed into emission in the infrared. On the far right is a comparison of 23 IXF with other dusty progenitors of supernovae, like 2017 EAW shown in blue, 2012 AW shown in purple, I believe. And as you can see, 23 IXF appears to have the dustiest progenitor we have ever seen. All right, in the same work, we also presented constraint on the presence of a binary companion for the progenitor. So the blue solid line, the blue dashed line on this left panel, this shows how the observed SED would be detectably modified by the presence of a hot companion. And what this indicates is, if the red supergiant star had a companion, it would have to be cooler than around 24,000 Kelvin, less luminous and less massive than these values indicated here. On the far right is the cartoon schematic of the CSM geometry around the progenitor. The innermost solid circle, it shows the location of the dense confined CSM that has been inferred from various studies of the early phase of the supernova. The outermost circle, solid circle here, that's the inner radius of the dust shell of the progenitor that has been obtained from result of the SED fitting. And the two dash circles, they denote the range of possible binary orbits for the companion of the progenitor if it had one. All right, from here on, I will mainly focus on our results of analyzing decades worth of infrared data. So this was from a paper that I led. So in this plot, you can see, sorry. So in the plot, you can see the extracted light curve of the progenitor, revealing this exquisite semi-regular variability of the star. This is in fact the first ever view of such variability in the final years prior to core collapse, of any progenitor star. Now, to drive the point that this variability is quite common in red supergiants, I've compiled here light curves in various wavelengths of red supergiants in different galaxies. These observed variations, they are considered to be pulsations driven by Kappa mechanism in the hydrogen ionization zone of these stars. And a feature of this mechanism is the light curve amplitude. It decreases with increasing wavelength. So as an example, this is the light curve of a galactic red supergiant, TB-GEM. And as you can see, the peak-to-peak amplitude in the V band, the visual band, is around 1.5 mag, and that decreases to roughly like 0.25 magnitude in the mid-infrared. On the left panel here is the infrared light curve amplitudes of the progenitor of 23 IXF. And as you can see, it clearly follows the expected trend, supporting the pulsation hypothesis of this of its observed variation. Now, to infer the properties of this progenitor star, we went for an approach which is completely independent of the more widely used SED fitting method, relying instead on the variability, solely on the variability of the progenitor star. So to that end, we used the better sampled mid-infrared light curve, which is shown here, extracted its power spectrum, shown in the top left panel here. We found the power peak at a period of around 1,090 days. And in the bottom panels, we modeled the observed near IR light curves of the progenitor with the same power spectrum to ascertain if the same periodicity is also present in these in the near IR. And as you can see, the sampling is very poor, but still the model seems to agree with the data, indicating a common driver for the observed variability in both the mid IR and the near IR. Thank you. All right. Now, a nice thing about these red supergiants is they are known to follow a period luminosity, or more precisely, a period MK relation. So what we can do is plug in the derived period of the progenitor star, and here straight away obtain its absolute K-band magnitude, which we found to be about minus 11.58 mag for the star. And secondly, the properties of the progenitor, particularly its mid-infrared brightness, color, light curve amplitude, period, and so on, they appear to be consistent with those of dusty OHIR red supergiant stars, which are indicated by these crosses in the CMD from Karambelka et al. So the plot basically shows the infrared variable stars. And the red circle, by the way, that's the location of our progenitor star. Now, the OGIR stars, they are known to have spectral type M4 and later. That's effective temperature range of around 3200 to 3500 Kelvin. So we assume that temperature range for our progenitor and applying the corresponding volumetric correction, we get a log L in the range 5.2 to 5.4. The gray shaded region here shows the possible location of the progenitor in the HR diagram. And gotcha. So these solid lines, they are the stellar evolutionary tracks. Comparing with that, we get an initial mass in the range 20 plus minus 4 times the mass of the sun. We can also use this empirical mass loss prescription for OHIR stars. And then we get a mass loss rate which is consistent with that obtained from the early hard X-ray observations of supernova. Now, a nice thing is that the end story of the progenitor, well, these are the various results, and there seems to be quite a variance there. So I think, it's just getting more exciting. I've run out of time, so I'm just gonna put up my conclusions and end here, and we'll be happy to take questions. Thank you.
Right, questions?
Thank you. It's great to see this quality of data. So if you were to have a progenitor of zero age-based sequence of 20 solar masses, that would mean it has a large helium core mass, which should then show itself as an enhanced oxygen in late time spectra. So have we looked at that yet? Presumably people have, but you would expect to actually see an elevated oxygen abundance there.
Yes, you're absolutely correct. So there was recently a paper led by Ferrari, I believe. They looked at the nebulous spectrum at about 250 days, and they tried to, I think there was some problem with measuring the oxygen doublet. So they instead looked at the ratio oxygen to calcium. And their constraint was, well, that's again model dependent, right? They got a constraint which is around like 15 solar masses. However, I think there were also this interesting simulation results that, particularly for massive stars, if there's this convective shell mixing, the oxygen shell can get diluted by calcium, and that would, like mimic a lower mass range for the progenitor.
More question?
Yes, thank you very much. Can you go back to the previous plot? Because I'm really not an expert on this field, but then what would be your explanation for having such a large variance in the initial mass of the progenitor, given that most of those estimates come from like more or less the same observations or like infrared observations? So I'm just wondering why from time to time you get like 20 solar mass, and for others you get like a low mass progenitor. What would be the explanation for having such a large uncertainties?
Yeah, that's a great question. The short answer is we don't know. And I think it would be great, like somebody could come up, with a way to kind of, consolidate all these results together. But of course, the funny bit is there are results there, like from Jacob Janssen, who did SED modeling, that also disagreed with another group who used SED modeling, and they found a smaller mass range. But I think it also boils down to how you actually treat your photometry, what kind of dust models you use in your SED modeling. So there's always like a variation there. And as I also mentioned, like the nebulous spectra, the hydrodynamic modeling of the light curves, like it's just varied. So I think like, I think this field is just really interesting just because we see this variation, right? So yeah.
Okay, I think we have to move on. Let's thank Monica again. The next talk will be online by Keiichi Maeda.
Yes, can you hear me?
Yes.
I cannot share my slides.
Okay, hold on.
I think you should switch off the already. Yeah.
Is this the online slide or? Are you sharing?
Yeah, I'm sharing. I think you can see it.
Right then. Yes, please go ahead.
Okay, so it's there. Okay, great. So I'm connecting from Japan. I'm Kitamada. Well, it's a hot summer here. It's evening, but still 33 degrees. I'm melting, but surviving. Anyway, let me get started. So happy to have the chance to present our work on nearby supernova with ALMA. Given the time limitation, I'm planning to focus on a couple of examples we have done. And okay, the massive star evolution in the final phase is a question here. It's unresolved. And this is something we want to tackle by studying properties of supernovae. And the first topic I'd like to introduce is the final evolution in the 100 to 1 year toward explosion in the accelerated nuclear burning stage, like oxygen burning, carbon burning, and so on. And I think this is indeed a very topical issue nowadays with the change in the paradigm in the last 5 years or so. As Daichi mentioned, we now have a hint that the so-called confined CSM, highly compact and dense CSM, just on the progenitor star, this can be quite common for type 2 supernovae with the red supergiant progenitors. And this is largely based on observation in the optical wavelengths. With the typical red supergiant wind for type 2 supernovae, it typically corresponds to something like 10 to the -3 solar mass per year in the last several decades. And however, deriving their CSM properties, CSM density from the optical data can be a bit tricky. And further, it's very likely that the optical signature in the optical wavelengths can be quite biased toward high density environment, high density CSM. And also, it's difficult to do the same exercise for type 1bc supernovae because of the expected lower density for type 1bc supernova CSM because of the high wind velocity. And so on. So we need something different. And the perfect alternative here is to go for radio because the synchrotron radio emission is exclusively coming from the interaction between the supernova ejector and the CSM. However, so this is example of a calculation of the synchrotron emission in such a situation with dense CSM shell just in the vicinity of the supernova progenitor. But you see in the centimeter wavelength, actually, the signature is blackout. The CSM density is too high. But if you go to millimeter, you can actually have the optical emission there. So this is an idea. So we have been conducting the millimeter observation with ALMA for infant supernovae as quickly as possible. So this is the thing I want to present here. And the first example here is type 1c 2020 OI, which is a kind of canonical type 1c supernova, carbon oxygen star explosion. It was discovered soon after the explosion, and we triggered ALMA also promptly just after the discovery. So we gathered data from epoch soon after the explosion. And this is type 1c, so with expected high wind velocity, the CSM density, CSM properties here correspond to the mass loss history in the last 1 year or so for this case. So this is something beyond what you can do with for type 2 in the optical wavelengths. And so we detected this object, and from the spectral energy distribution, we are sure that it was in the optical scene regime in the ALMA bands. And because this is in the optical scene, roughly speaking, the flux evolution translate into the CSM radial distribution. So the red point here the data from ALMA. Well, ALMA is expensive, so we only have got 4 data points, but you see it's not a straight line. So this strongly indicates that the CSM radial distribution, density distribution is not a power law, not a single power law. So rather we see that this is showing something like a zigzag evolution. And applying the synchronous emission model, we converted these data points, including the lower frequency data, to the mass loss history for this object. And it's like this on the right panel, the red lines. And you see the first, the overall mass loss rate here is actually quite high in the last years to a decade, which matched well to what we inferred for type 2 supernova progenitors from the optical data. It's kind of connecting. And further, we see some variability here in sub-year timescale. We believe this variability is actually real, not an artifact. So this suggests that the progenitor, this is carbon oxygen star progenitor, did show activity in the dynamical timescale, not in the thermal timescale. So this is something we have to consider in studying the final evolution of massive stars. Okay, so I think I have a couple of minutes or 3 minutes. So changing the topic. So another example I want to talk a bit is the implication for the binary evolution. And here I'm focusing on the mass loss history in the timescale of 100,000 years before the explosion. And this 2018 IBC is a peculiar type 2L object. We don't know the nature of the progenitor and so on. Again, it was discovered soon after the explosion, and we triggered ALMA promptly. And from diagnosing, okay, couple of minutes. Okay, from diagnosing radio properties, peak luminosity versus peak time, it actually was similar to type 2b supernova, which infers the ejector itself was similar to type 2b ejector, like helium star with a small amount of hydrogen-rich envelope attached. And applying this kind of model, we could reproduce the much wavelength observation in the optical, X-ray, and radio ALMA data only by the supernova CSM interaction model. So it didn't show the contribution from nickel and so on. This suggests the CSM density was actually quite high. And what we derived was actually the CSM density just in the vicinity of the supernova progenitor was actually quite high, order magnitude, at least an order magnitude higher than canonical type 2 progenitor like 93J. This finding may indeed fit into the binary evolution sequence with the initial separation as a controlling parameter. And if the binary is sufficiently close initially, the binary interaction should take place something like 10,000 years, a million years before the explosion. And the system should be detached at the time of the explosion for such canonical stripped envelope supernovae. But if the separation is large, they can interact certain years before the explosion. In this case, you still lead a small amount of hydrogen-rich envelope on top of the helium progenitor, helium star progenitor. So this is consistent with type 2L. And also in such a case, because the system is still filling the loss lobe at the time of the explosion, it should show the high mass loss rate. This is again consistent with the data. And the one prediction here, another prediction here is that such a model should actually have had the main binary interaction about 1,000 years before the explosion. So this should actually form the detached CSM shell somewhere. And so we should expect the radio actually should be brightening, should show rebrightening about 1 to 2 years after the explosion. If the model is correct. And indeed, for this guy, we did find such a brightening radio, both in centimeter and also in Alma, like this. So this is 200 days after the explosion fading, but this is more than 1,000 days after the explosion. It's again brightening. This suggests dense CSM was around, which is consistent with the idea that the main binary interaction was actually happening something like 1,000 years before the explosion for this guy. So I think I've got to stop here. So thank you very much. I'm stopping here.
Thank you. Any questions for Keiichi? No questions?
So why 1,000 years? What was happening at that time that's different than any other time?
In theory or in observation, you mean?
Sorry?
In theory or in observation?
Well, I mean, I don't know. What was physically happening?
Okay, so in observation, we saw the radio brightening about a couple of years after the explosion. So comparing this to the time scale, assuming the wind velocity of I think something like 20 kilometers per second for the red supergiant or yellow supergiant progenitor, because we expect this guy should extend it. So in this case, the observation, to explain the observation, we need the eruption of the CSM shell something like 1,000 years before the explosion. And in theory, to explain the nature, the radio property of this guy, we expect, actually in the binary scenario, we expect the main interaction actually must take place something like 1,000 years before the explosion. Otherwise, we don't explain the amount of the hydrogen-rich envelope left, and also the CSM density just around the progenitor star.
Okay, let's thank Keiichi again. Thank you. And next we have Martin Solar. Please slide. Okay, please.
I'm a PhD student at the Adam Mizrahi University, and today I'm going to show you how I reached the conclusion that most of the progenitor of type 1c supernovae are formed and evolved in binary system from an observational approach and using a large sample, a statistical large sample. So let's get started in how a supernova is defined. And this is during the early phase of the explosion, when the optical light is maximum and the ejecta is optically thick. As type 2 supernova is classified as, a supernova is classified given its appearance in the spectra. So a type 2 supernova, it shows features of hydrogen in the spectrum. That's because the star prior to the explosion, it preserved the envelope of helium and hydrogen prior to the explosion. On the other hand, a type 1c supernova, it doesn't show features of hydrogen, neither helium in the spectrum. That's because the star prior to the explosion and the envelope was removed from the envelope was removed prior to the explosion. And there are two main candidates possible for this that could cause this. First one, it's a very massive star in which the star itself is responsible to blowing away the outer layers. The second scenario is actually a binary system in which the less massive star is responsible to strip away the outer layers, and this effect is called mass transfer, known as the binary interaction. So it's essential, and we should take care about the initial mass of the progenitor. And we use the environment of supernova in order to constrain the initial mass. That's going to be thanks to the CO, carbon monoxide emission line, because this is a tracer of the molecular hydrogen. And the molecular hydrogen, the giant molecular clouds are composed of molecular hydrogen. And we locate the supernova at the giant molecular cloud parents. It's important to mention that the typical sizes of molecular clouds are of the order of 100 parsecs. And combining these two approaches, we get at the supernova pixel position the molecular gas surface density. Okay, so in this, and we use the molecular gas surface density as a tracer of the progenitor lifetime. And because it is known that the equivalent width, in this plot, it is shown the molecular gas surface density as a function of the equivalent width of H alpha, and the equivalent width of H alpha measures the strength of H alpha divided by the continuum. So that means for higher values, it will dominated by younger and massive stars. And actually we see this, so the equivalent width is a tracer of the stellar population age. And so as you can see, for higher values of the equivalent width of H alpha, it will associated with higher values of molecular gas surface density. That means associated with low progenitor lifetimes. And this is going to be a key approach in order to estimate the initial mass of the type 1c supernova progenitors. So we will use ALMA observation in order to reach the, in order to observe the molecular clouds. And we use data from FANGS and from the ACOS surveys. These are nearby galaxies within 20 megaparsecs from FANGS and 50 for ACOS. We gather a total of 30 type 2 supernovae and 21 1c supernovae. And I have to highlight that this is a statistical study that we plan to study the supernova population, compare these two supernova types, not individual supernova progenitors. And it is assumed that the molecular cloud decays as a function of time given by this equation, in which the molecular gas surface density is the value of the supernova environment. Sigma 0 is just a normalization constant. TSN is the lifetime of the supernova progenitor. Tau GMC is the lifetime of the molecular cloud. And as you can see in this plot, the molecular cloud decays as a function of time at the supernova progenitor after the starburst. And going straight to the results, skipping all the computation, and you can see in this cumulative distribution function the environments of molecular gas surface density for both types of supernovae. And I will say that they are located in quite similar environments. Actually, if we go to the results, they are in completely agreement. So doing a little bit of algebra from the equation that I showed you 2 slides before, we got that the lifetime difference for both supernovae is only 0.4 plus minus 4.3 megayears, and that in time scales of supernova progenitors in massive stars is quite low, I would say, right? And we know it is well constrained the initial mass of type 2 supernova progenitors. That's within 8 and 18 solar masses. So it is suggest that it is interpret that the progenitor of type 1c supernovae are actually binaries, as they have similar initial masses. And at this moment of the presentation, you may wonder how is possible to make such a strong claim, right? So in order to justify the data sample, the sample size of our data, we make use of the Zaparta's 2017 simulations, which is it is shown a beautiful initial mass lifetime relation for a single star. However, massive stars are formed and evolve in binary systems. So these beautiful relations, now it converts to a 2-dimensional distribution function that takes in consideration the initial mass function, the IMF, and the binarity fraction. So our plan is to compute if it is possible to distinguish between very massive stars and less massive stars. So the red region shows the less massive star, the within 6 and 18 solar masses given by the type 2 supernovae, and the blue region is constrained by very massive star. In this In this context, very massive stars are higher than 18 solar masses. So the research question is it possible to distinguish between both distribution? The short answer is yes. The important question is how. And this is going to be thanks to Monte Carlo simulations and this equation that I showed you a few slides before. So for each supernova, we get the initial mass. We can compute the lifetime and therefore we can compute finally the molecular gas surface density. And we test for both regions. I told you this within 6 and 18 and higher than 18. We compute the Kolmogorov-Smirnov test for both regions, and if it is possible to reject the null hypothesis. So for our current sample of 30 type 2 supernovae and 21 type 3 supernovae, from this plot, it is possible to appreciate that our statistical significance is a 95% in order to reject the null hypothesis that the massive stars, that progenitors of type 1c supernovae come from very massive stars. So this is how I finish with the presentation. We use the molecular gas surface density as a tracer of the progenitor lifetime. We find these two supernova population in very similar conditions. So they have similar lifetime. We have this similar lifetime, and we conclude, as is in the title, that the progenitor of type 1c supernovae are binary system. Thanks for your attention.
Thank you. Very interesting. Questions?
Hi, thank you for the talk. I was wondering, in your very first plot, you're showing this relationship between the age and the molecular cloud or the CO amount. There are quite large error bars on this. And can you actually determine the age of the cloud based on the molecular density? So here you don't, you just have the relationship, but earlier on you have these error bars on there.
Sorry?
Yeah. The other way, sorry. Yeah. Yeah, can you really get an age from this? Because I can fit a straight line through here as well and get a relationship.
Yeah, actually, it is compute this correlation test, and these are in very good agreement. But are you talking about, do you mean the error bars, these ones?
Yes.
These are non-detection, are dominated by non-detection, in which the molecular gas surface density reach values lower than 0.
Yeah, but even the higher end, the top end, you can, like, can you get an actual, this is a relationship, or is this just, there's a feature here because we don't have the accuracy to do this measurement? Maybe someone else knows this better. I'm just, yeah.
Have you looked at doing your same analysis, the same galaxies, to sites of Wolf-Rayet stars, which you know are massive, and demonstrate that you can recover what you would expect, because they're kind of a surrogate of a massive 1C population, for example?
No, I have not, but it could be interesting to study. Yes.
Okay, see one more question.
I need to check the data sample.
Yeah, thanks for the great talk. So I have a question about the spatial resolution via ALMA and the Muse observations. And is there any chance the birthplace of the supernova is different from the explosion sites?
What, sorry?
So what's the spatial resolution of ALMA and Muse observations? And then is there any chance that the supernova birthplace is different from the explosion sites? So you're getting different environment estimates.
The resolution for ALMA in nearby galaxies, this is, sorry, is for FANGs. These are lower, the distance for FANGs are lower than 20 megaparsecs. That means that it is possible to reach to solve the spatial scales of molecular clouds. So that's less than 1 arc second.
Okay.
And for Muse is even lower.
Okay, I think we have to move on. Let's thank Martin again. Next we have Tinyanon. Please.
Hello, good morning, everyone. My name is Gal Samaphon Tinyanon. I'm a staff researcher now at the National Astronomical Research Institute of Thailand. Super excited today to tell you all about my checkup with old friend 2014C with James Webb Space Telescope. So for brief context, for those of you who are not aware of the supernova, this is a supernova called 2014C. Exploded in 2014 as a hydrogen-poor, helium-rich type 1b supernova. And then it went behind the sun for 2 or 3 months and then came back with booming bright hydrogen. So we think that what we see is the supernova shock running into the hydrogen envelope that has been lost from the progenitor star. And this is the spectroscopic evolution that we see in the supernova. At early time, we see a spectrum that looks very similar to a typical type 1b. And then after its excursion behind the sun, came back with this booming H alpha. And this spectral feature, bright H alpha, is still here today. So my previous work on the supernova has been looking at it in the infrared, because when you have a strong interaction, the dust that is inside the circumstellar medium also gets heated by the shock interaction and re-emit in the infrared. So this is a plot from my 2019 paper showing the luminosity evolution of the supernova based on spacer observation. And to try to model this, I used a semi-analytic model by Keiichi made 2012 to try to constrain the density profile of the CSM, and the main result from that paper is that the bolometric luminosity light curve is very well explained by this very typical wind-like R to the -2 spectral profile. On the right here is just a pretty picture from Paloma near infrared, plus 2 bands from spacer, just to demonstrate even back in 2017, 2018, how red the supernova already is. It's barely detected in J and H, and then it's booming bright in spacer 3 to 5 micron bands. So, seeing this kind of evolution, we thought it was a kind of a no-brainer to ask for JWST observations in the mid-infrared. So we put in a cycle 1 proposal. But before we get to that, I will also show a more recent. That's really interesting. The actual spectrum went away from this, but believe me, this is a very nice plot to the actual data. Pretty sure I checked this. But anyhow, we had 2 observations of the supernova with Keck-Nairus, one from about 1700 days post-explosion. So this was in my 2019 paper. And then we follow it up as part of the Keck infrared transient survey. So if you're interested in that, talk to me as well. This is from 3,800 days after the explosion. And this is the work done by my new PhD student, Kittipong Wangnop at NARIT. And what he found is that, interestingly enough, this is the helium 1.083 line. So this is a strongest helium line we have. Initially, we have this like very broad component with velocity of about 5,800 kilometers per second. And then there are these 2 kind of like intermediate width components with 1,700 kilometers per second. And then we have like this unresolved host line. Fast forward 200 days, these components are still here, but the velocities of the broader component decreased from 5,800 to about 2,700 kilometers per second, while this intermediate width remains at the same velocity, about 1,700. So we are working on a full analysis of this and what the implications these measurements have on the CSM geometry of the object. But to the main event for JWC observation, so we got observations of the supernova with near spec IFU and also MIRI MRS. The observations were done MRS in July last year and then near spec in December. So the data are public now on mass. You can go look at it. These are just kind of a stack in these 4 filters, and already demonstrating that you know, if you hear any JWST talk on supernova with MRS data, the main bottom line is that background subtraction is a massive pain. MRS has a thermal background from zodiacal light from the telescope itself, especially towards the end, the red end of the spectral coverage. On top of that, for us poor nearby supernova observers, we also have the galaxy to deal with. So this is the kind of like faint, not really faint, diffuse emission from the host galaxy that is relatively bright and also spatially varying. You can see this kind of like elongated structure behind 2014C. Kind of fortunately for this object, the supernova itself is still extremely bright in all bands. So the issue is somewhat mitigated by that. But yeah, if you want to know more about how to do MRS background subtraction, I would be happy to talk at length. So this is a result. This is a spectrum plotted in FNU of the supernova, and you can see right away this is beautiful dust continuum with clear feature from silicate dust at around 10 and 18 microns. So in attempt to fit this with a dust model, first I need a small warm component just to take care of the near infrared flux. And then for the mid infrared flux, it's very well fitted by just 2 components, one with silicate and one with just carbon dust. These 2 have fairly similar temperature, around 200 to 300 Kelvin. And the key finding here is the mass involved in these 2 components is quite high. The total mass now is around 0.07 solar masses total. And another interesting thing about the dust emission at this phase is that it is now relatively optically thin. The optical depth of this is around 0.1 to 0.2 now, which is very low compared to at early phases. And because of this, we think that this is all the dust that is involved in the supernova now. So great question always for dust emission in CSM supernova is that like is this new, or is this from the CSM that will get destroyed by the shock? So we have tried a couple of analyses to try to pinpoint the origin. One is that we look at the CSM profile. So this is the total luminosity integrated from the JWC observation. And much to my surprise, this is just plotted down to the previous plot with the model fitted to the Spitzer data, and JWC point essentially lands pretty much right on top of it. So what this shows is that the CSM we are interacting with, that 14C is interacting with, is still the same component as it was before. So it is really unlikely that we are encountering like a denser shell of CSM and see more dust from that. So yeah, this demonstrates the evolution of the dust mass from before with Spitzer up to JWC epoch now. And you can see this like 10 times increase in mass. And we are more inclined to say now that it is actually like new dust that is forming behind the shock front and the reverse shock. And if it is so, then it's super exciting because it points to the supernovae being on track to dominate dust formation in the early universe. And this is a plot from Melissa Shabanda 2023 paper that look at these 2 supernovae, 04ET, sorry, yes, 04ET and 17EAW, to show that dust mass observed in supernovae indeed grow from very low at early epochs to very high that we saw in 87A. So I will running out of time, so I will leave my conclusion up and take questions.
Thank you. Great talk.
Hey, thanks. Nice talk. So as you mentioned, channel 4 subtraction is a huge pain. Have you, and your dust fits are really nice, but have you tried doing your dust fits without including the channel 4 data to see how much the mass varies?
That's a great point. I have not tried that. I can try to do it. Let's see. So so for this data set, the background subtraction is kind of, the trouble is a bit mitigated because I have dedicated background observation. But still, if I plot the unsubtracted version, it will just shoot through the roof. So yeah, I'll try that.
Thanks.
Thanks for the nice talk. I was just wondering on the spectra, the spectra we couldn't see.
Yeah. I don't know what's going on.
Yeah, this one. So the narrow components you're seeing are coming, you reckon, are coming from CSM. So I mean the gold yellow colored one, that's CSM. It's yeah, that's you see a blue shifted component, but you don't see anything on the red side. What's the geometry, or what are your thoughts on that?
Yeah, it's unclear. So there is this let's see. Yes, blue shifted component. I think there is a paper by a different group. I forgot now. I think it's a UT Austin group doing the same analysis on H alpha profile and also this helium line. And I think they said it could be some sort of plume that is like kind of pointing towards us. Yeah, definitely we'll have to revisit this.
That's beautiful data. With your estimate of the dust mass now, it is a stripped progenitor. Can you give an estimate as to what the mass of the progenitor was at the time of the explosion, just roughly?
Right, for the progenitor, I think it would be difficult to say with this data set. The problem with 14C is that, kind of annoyingly enough, is it doesn't have good observations in the optical. So we don't have those, like classic rise time and like peak brightness in the optical that we can fit with the classical models that Daiichi presented. I think the best estimate is like around a few solar masses. So we don't think that this is from a very massive progenitor star.
Okay.
Yeah, and I should say as well, kind of following along with all the discussion this morning, is that we really think that this is from binary interaction.
Yeah. Thank you.
All right, let's think again.
Right, thank you.
Next, we have Christina Humina.
Yes, hello, my name is Kristiina Humina and I'm from the University of Turku, Finland. And my talk today will be about the late time evolution of the interacting stripped envelope supernova 2017 DIO. And even though we have already heard quite a good introduction to supernovae, I will give you a brief one. So supernovae are the explosive deaths of stars, and they can be categorized into different types depending on what elements they show in the spectra. So for example, the type 2 supernovae have hydrogen in the spectra, while type 1 supernovae do not. And these can then be further subcategorized into different types. And in some cases, a star can lose its hydrogen and even its helium envelopes before explosion, creating this stripped envelope supernova. And the reason for this might be, or is from mass loss, and the mass loss mechanism can vary from stellar winds to binary interaction, eruptions, and so on. And the supernova I will be talking to you about today, 2017 DIO, was classified as a type 1c supernova. So it has lost all of its hydrogen and helium envelopes before explosion, and does not show any hydrogen or helium absorption lines in spectra. And it later on evolves into an interacting type 2n supernovae, where the n stands for narrow lines. And interacting supernovae are supernovae whose ejecta interact with circumstellar medium CSM. And interacting supernovae come in many different shapes and forms, like we just saw one of them. And if you're interested in other interacting supernovae, you should go check out Kangas and Pyykkinen's posters tomorrow. And so back to 2017 DIO. Here I have its entire spectral sequence. And in this, the epochs here are marked days from R peak, and then in parentheses days from explosion. And in this first few spectra, we see this spectra that resembles other type 1c supernovae. But then on top of that, we also have these narrow hydrogen emission lines that come from the interaction. So as these narrow emission lines are hydrogen, it basically means that the supernova is interacting with hydrogen-rich CSM. Then roughly 25 days from the explosion, the interaction starts to dominate and we no longer see the underlying supernova type. And then thereon, we get this type 2n spectrum, and it has this bump here in the blue, and then it also has this calcium near infrared triplet here in the red. Right, and one of the reasons why we want to study 2017 DIO is because we want to find out more about its mass loss mechanism and also what kind of progenitor can produce such a supernova. And to do this, I have taken a closer look at the hydrogen emission lines, as those are one of the signature features that arise from the interaction. So here I have plotted the H-alpha profile on top of each other from different epochs to better see how it evolves. And this can tell us about the strength of the interaction. So in this first few spectra, first few epochs, we don't really see much of a change. It's just this narrow emission line. But then roughly 44 days from the explosion, we notice that it starts to broaden up, and this is when the interaction starts to get stronger. And it grows all the way till 90 days, whereafter it starts to, the profile starts to narrow down again, and that's when the interaction gets weaker again. So strongest roughly for 90 days from explosion, and then narrows down again and gets weaker. And this is also consistent with the H-alpha luminosity, which is plotted here in red. So the H-alpha luminosity starts to grow roughly 44 days from the explosion, which is when the line starts to broaden up. And then after 90 days, it starts to decline, which is also when the profile starts to narrow. So that is consistent with the interaction getting stronger. And in this plot, I have also plotted the H-alpha H-beta ratio, the Balmer decrement. And the Balmer decrement has this theoretical value for different cases. And if we see some deviations from this, that might mean that something is going on. And in this first few spectra, it could tell, or first few epochs, it could tell us about the density of the CSM, but we don't really see any huge fluctuations here. So yeah. And then here at late times, we know that the Balmer decrement is rising quite a bit. And this may be related to an infrared excess that we have here, which I will be talking on later. Right, and then the light curves of 2017 DIO. So 2017 DIO shows this double peaked feature where we believe that the first peak is from the supernova, and the second peak, the huge peak that is mostly visible there, is from the interaction. And this is just a close-up for the first 100 days, and we can basically see the double peak best here in G band, and then this second rise that starts somewhere here is also consistent with the timing when the interaction starts to dominate the spectra. So we believe that most of the light curves are powered by interaction, but we do also have a component of CSM. Yeah, and otherwise 2017 DIO has really long rises to peak, roughly 70 days, depending on which band we are looking. And then, as I mentioned, we also have this excess here in near and mid-infrared at late times. So when I'm doing some light curve modeling, I'm only using the optical bands so that I don't take into account the near infrared or the excess in infrared. And to do light curve modeling, I am using MOSFET, and I'm using models that have the CSM and nickel mass or nickel in it. And I'm using also models with both the shell and the wind models. Yeah, and this is still a bit of a work in progress, but why I'm doing this modeling is to find out more or different properties of the CSM and the supernova. For example, with this, we can find out the nickel mass, CSM mass, ejecta mass, and radius, and many other things as well. And this is done to find out mostly about the CSM that is like nearby the supernova. And then, as I mentioned earlier, we also have this infrared excess, and this infrared excess could be due to either pre-existing dust or newly formed dust. And if it is because of the pre-existing dust, then that means that it would lie further away from the explosion site compared to the CSM. And so by studying this infrared excess, we might be able to find out more about the earlier mass loss history of the progenitor. And here I just have plotted the spectral energy distribution plots of different near-infrared epochs. And we note that here in the beginning, we don't really have any excess, while then at later time, the excess here is much stronger than the supernova itself. And here I also have the extracted magnitudes of the excess. Right, so in conclusion, 2017 DIO is a type 1c interacting with hydrogen-rich CSM, and this means that it must somehow retain the hydrogen-rich CMS close by, while simultaneously getting rid of the helium layer. And this could be done either by stripping by binary or eruptions. And it is evident that some modeling of the progenitor evolution is needed to better understand what is happening. And then the light curve modeling is used to understand the mass loss history of the progenitor, optical bands to probe the nearby CSM, and then the infrared excess, if it is related to the dust or the pre-existing dust, then that is used to explore the earlier mass loss history of the progenitor. Thanks.
Questions?
Thank you for the very nice talk. I wanted to know, like, when you tried to do the MOSFET modeling, since you have initially nickel dominated and then like interaction both, how much nickel mass do you get from your modeling?
So the modeling that I showed here, I wouldn't really trust at the moment. I have also calculated the nickel mass myself, but I do not remember the numbers. I can tell you afterwards if you're interested.
Okay.
Yeah.
Thank you.
I have a quick question on MOSFET. I understand it's still work in progress, but I think I read the supernova ejecta mass was smaller than the CSM mass. If I read it correctly, it seems like it's really hard to get that kind of progenitor system, I think. So do you have any ideas, or like, is it just a bad fit?
Yeah, I would still say that the numbers that you saw there aren't really representing the situation as it should be.
Really nice talk. Maybe it's worth considering that this hydrogen-rich CSM is not necessarily coming from the exploding star, but from the companion. If you look, for example, at Ithakar, it has the star which might go an explosion is next to a companion which is spewing a lot of gas. It's hydrogen-rich. It's potentially accreted mass in the past. So just something to keep in mind.
Yeah, that is
if
one
it's a
of the things that we have considered as well.
Okay.
Another question or comment?
Yeah, I was going in a similar direction. Also, the question is, could you explain by binary stripping to really get fully off the helium layer? Because apparently, as far as I know, that is quite hard to do, right? So you can strip the star down to a helium star, but stripping it further only with binary interaction is probably quite hard to explain. And do you have any evidence of a companion in the data that you have?
I don't think that there is any evidence of a companion, but like as he mentioned here, one of the ways to get rid of at least the hydrogen would be like stripping by binary, and then it is not said that the hydrogen that we see or the CSM is from the progenitor that we have here. I do not know how the helium layer is stripped entirely. I don't know if anyone really knows how it's done, so I cannot answer what kind of things would need to be done there.
Okay, I think we have to move on. Thank you so much again, Christina. Next, we have Gustav Das connecting online. Are you there? Okay, go ahead and share your
Do you hear me?
Yes.
Okay. Oops. Sorry, give me a minute. Okay. Do you see the title?
Please go ahead.
Hello. Okay, perfect. Okay, hi, I'm Gustav. I'm a rising fifth-year PhD student at Caltech, working with Professor Mansi Kasliwal in the Zwicky Transient Facility collaboration. So my talk today is on this spectacular transient, SN 2023 SAW, which we believe to be an ultrastrip nickel pore supernovae from a low-mass progenitor. If you're interested, do scan here for the QR code for the link to the paper. It's almost 3 a.m. here, so I hope I can pull together a coherent talk. So I'll start with a brief introduction on what is an ultrastrip supernovae. So I guess most people in this room are already familiar with what is a strip envelope supernovae. A possible channel, as was discussed earlier, is that you have a binary star system where you have one of these stars which overfills its Roche lobe and then is stripped of its outer envelope and then finally explodes as something called a type 1 BC supernovae. So usually stripped envelope supernovae have ejecta masses of around 2 to 5 solar masses. But if we wanted to get to very low ejecta masses, say even less than 1 solar mass, what would be possible ways? As was suggested, that it's quite hard to strip stars to its very bone. So for that, we require that the stripping be very extreme, and then that the companion radius be very small. So one possible formation channel to do this is through something called an ultrastrip supernovae. So the idea is that the surviving companion also overfills its Roche lobe and then explodes as something called an ultrastrip supernovae. So this is one of the leading, or this is one of the formation channel for double neutron star systems as well. So we believe SN 2023 SAW is such an ultrastrip supernovae candidate. So the story starts in around 7th December 2023 last year. So it was very rapidly declining early on with almost 0.45 magnitude per day decline. It was faint red. So naturally it got the kilonova community excited and we followed it up as a kilonova candidate. The initial spectrum with broad helium-1 lines ruled out the kilonova picture, but then we were still puzzled by what the nature of this transient could be. So the initial decline did stop around after 12 days post-peak with a more regular stripped envelope-like decline rate. But the initial very rapid decline of this transient remained kind of a mystery so as to what could be the possible progenitor channel and formation pathway of this transient. So just to again highlight how unique this object was, in this plot I have the peak magnitude on the x-axis, on the y-axis, and the time above half maximum in the x-axis. And you can see here all the different supernovae discovered by ZTF and how 23 ZA in the red cross stands out both as being subluminous as well as being very fast evolving. So the fact that it's fast evolving kind of gives a hint that possibly you have lower ejecta mass. So as I already mentioned, when we obtained spectra very early on, we saw that there were very strong helium-1 absorption lines and was classified as a type 1b supernovae based on the photospheric spectra. There are other interesting things about this spectra. For example, there were strong near-infrared lines as early as 2.5 days. Also, we saw that there was some redshifted component of the helium-1 line, likely suggesting that there's some asymmetry in the ejecta. The most interesting part about the spectrum was that when we followed it up at around 30 days post-peak, we find that narrow interacting helium-1 lines have emerged at around the 30 days post-peak. And unlike like 1B and 1C and supernovae, we do not see this narrow lines in the spectrum taken at early phases. So there could be a couple of scenarios for this. One is that in this binary stripping, you have a CSM that's placed at a large distance from the binary system, and it takes around a month for the ejecta to collide with the CSM and for the interaction to be visible. The other, personally, I feel more likely scenario is that in this binary stripping through L2 point, you are likely to form a CSM that forms a torus-like distribution around the binary system. So initially, if you are not looking at the right line of sight, you are probing the photosphere, which has a broad component. And then over time, as the photosphere recedes, you then finally start seeing the interaction with around intermediate velocities of 1,000 kilometers per second, as was seen for this object. So we also obtained a spectrum with the Keck cosmic wave imager to understand the host environment. And as you can see, we find that the objects suffer significant host extinction, as well as we conclude that the star formation rate of this object should favor more massive star origin. Now moving on to the light curve modeling, we first do a radiation hydrodynamics approach where we take helium stars modeled through binary stripping, evolve to oxygen neon burning, and then explode them using the supernova explosion code. So through the evolution, it has undergone multiple rounds of low overflow. The second approach we try is that we do analytical fitting as a combination of shock cooling plus nickel powered. And we find that both this modeling gives us some kind of consistent values. We get very low ejecta mass of just around 0.5 solar mass, and we get extremely low nickel mass, which is just 0.002 solar mass, which is the lowest nickel mass we have seen in any stripped envelope supernovae. So from this phase plot, you see that here is the canonical stripped envelope supernovae, and 23 ZA lies as a very nickel poor ultra strip supernova. So how do you explain such very low nickel mass and low ejecta mass? One is possible that it's a fallback of a massive star, but then we consistently see that the velocities are of the order of 10,000 kilometers per second or higher, so likely ruling out this scenario. The other more natural explanation is it's a ultra strip core collapse of a progenitor less than 10 solar mass. So various binary star and single star evolutions have shown that you expect very low nickel mass for extremely low progenitors like 8 to 10 solar masses. Also, our radiation hydrodynamic simulations with MESA and SNEC shows that it's likely the low mass around we explode a 2.5 solar mass helium star with SNEC, and it kind of gives a very decent match to the observed light curve. Also, there was a similar paper on this object a few weeks ago from Moore et al. 2024, and they also conclude that the progenitor channel is likely something coming from around a 7.5 to 9 mass system in a binary star system. So to summarize, I'd say that 23 ZA, as I mentioned, is very extremely faint and rapidly evolving. It starts showing narrow helium-1 interacting lines, which were absent at early phases. Radiation hydrodynamics and analytical modeling suggest that it's likely an ultra-strip supernovae with very, very low nickel mass, and that it's coming from a 7.5 to 10 solar mass progenitor in a binary system. So I'd like to end with a couple of thoughts. So it has been seen observationally that the nickel mass distribution of stripped envelope supernovae is significantly higher than the nickel mass distribution of type 2 supernovae. So while there are many explanations for this, I guess one possible thing is that we are biased against discovering 23 ZA-like events. because if you are stripped and you have low nickel mass, then you are faint as well as fast, and that is kind of the hardest class of objects to discover and follow up. And the other thing is progenitors in the 7.5 to 10 solar mass should account for like 30 to 40% of all massive stars. So why are 23s all like transients so rare? Or putting it another way, what do this low mass stars in binary systems explode as? Thank you.
Thank you.
Yeah, thanks for that, Stuart Ryder, Macquarie University. I think in your KCWI map, you reported a star formation rate of 1.4 by 10 to the minus 2 solar masses per year. Is that that's not for the host, is it, or is that just some local star formation?
It's for the local environment. Yes.
Is it per square kiloparsec, or is it just over the region of the supernova itself?
It is around a circle of some radius. I forgot the exact number.
Okay. It just seemed right below the galaxy. I didn't see the area units. Okay.
Yes. Yeah, the unit should be in the paper, right? Yeah.
Thanks for the great talk. This is Daichi Shiramazu from Harvard CFA. So any thoughts on whether this could be an electron capture supernova?
Yeah, we do discuss the scenario in the paper. So I think a couple of things do not match up. So the models, at least, I think we refer to Takashi Moriya's models, and I think they were around 10 times fainter than what we have for 23 ZOG. And also like the late time nickel tail that we see was hard to explain in the scenario. But it cannot be entirely ruled out. Yeah.
Okay, thank you. I think we have run out of time. In the schedule, we have this 1 minute poster flash talk, but let's move it a bit later. I think it's a bit ambitious to put it in the schedule. But anyway, we'll meet again here at 1:30 for the next session. Thank you so much. And thank again all the speakers this morning.
Is it on now? Yes. Okay, so it is 1:30 and we should be kicking off the next session. To start this off, we have Anjasha Gangopadhyay, and been informed that this is close enough for a pronunciation, from Stockholm University, and she's going to talk to us about interacting supernovae. Go right ahead.
Thank you. Yeah. Hello, everyone. So I am Anjasha Gangopadhyay, and I have been, thank you, Hanin and SOC, for giving me this opportunity to review the interacting supernovae class, which is a huge class, but I'd like to summarize. And we have been listening a little bit about this from the morning. So by interacting supernovae are the group of supernovae that show narrow emission lines of hydrogen, helium, carbon, or oxygen due to interaction with a nearby dense circumstellar medium. So if you look on the left, then this is the one which is 2N and show narrow emission lines of hydrogen. While if you look into the right side, there are groups which show narrow emission lines of helium, and we call them 1BNs. And those that show narrow helium emission, emission lines of carbon, nitrogen, oxygen, we call them 1CNs. So if you look into the statistics from Perle et al. 2020, you see that type 2N constitutes about 14.2% of the core collapse, and 1BN are 9.2%, while 1CN is a very new class with a handful of 10 or 15 events supernovae so far. And if you look into the peak absolute magnitude versus the rest frame, you see that 2Ns and 1BNs are on the relatively luminous area because of the interaction with the dense circumstellar medium, and they might have fast rise depending on the amount of circumstellar medium and their density. So the important challenge here is to probe the progenitor systems of this group of supernovae. So if you trace the progenitor with their mass loss mechanism, you know that 1B, 1C are the ones with full-bright stars, and then we have these cases of 2Ns which are thought to be originated from luminous blue variable stars. But if you do a single star mapping, then there are not 2Ns directly mapped to the number of LBB progenitors. So of course, there are questions that these are not only from single stars, and what we have heard that it could be from binary evolution, binary scenario giving rise to these kind of explosions. Now, if you want to know the physics behind this scenario, so we have a supernova ejecta moving out, interacting with a dense circumstellar medium. You see there are 4 zones there corresponding to the pre-shock circumstellar medium, the interaction between the supernova ejecta with the dense circumstellar medium, and a cold dense shell formed between zone 2 and zone 3. And then there is the freely expanding supernova ejecta in zone 4. And any of this can contribute to a type 2N supernova depending on the density of the circumstellar medium. So, but life is not that ideal, and we don't have a spherical symmetry always. So of course, asymmetries exist in these kind of systems. So I start with a sample of 2N, which is a study done by Milholm et al. 2020, where he studied and compiled a group of type 2N supernovae light curves. And he found that the supernovae 2N are actually a diverse and a heterogeneous class. So there are 2 specific sectors dividing them, the slow decliners and the fast decliners, if you see on the top panel. And then there are, if you look into the average absolute magnitude, then it's -18 to -19 mag. But then there are superluminous 2Ns also, which are above -21 mag, and there are nearly 3 in his sample. But then he also found that there are a couple of them with the bumpy light curve, as you show in the right-hand side, as you see in the right-hand side, and we see small bumps appearing in the light curve features, which hints towards the asymmetric CSM structure. Now, so when we talk about 2N, so 2N is actually a huge class. So there are long-lasting supernovae of 2N. There are superluminous supernovae 2N. There are 2NPs where you see the light curve as 2Ps, but then they show interaction signatures. And then there are ones with the compact circumstellar medium, and we have some recent examples where thermonuclear supernova interact with their nearby circumstellar medium, and we have 1A CSMs. So looking into one such class, I'm showing you one event 2012 AB. So this is one of the classical example where you see that the light curve lasted up to 1200 days post explosion, and you see a multi-staged light curve evolution here. And then if you look into the absolute magnitude scale, it is almost about minus 20 mag, and then it is a standard long-lasting type 2N class. Now, when we have a spectral evolution, we try to model the H alpha profile for these cases to find out the geometry of the circumstellar medium. So we try to fit the H alpha models here, H alpha profiles here with a number of Lorentzian and Gaussian components. And we see a narrow emission from a pre-shock sorry, how do I go back? Okay, is it this way? Oh, how do I go back? Okay, this. The red arrow. Red arrow. Okay. Yeah. So we have this narrow emission from the pre-shock circumstellar medium. You see a broad emission which is coming out from most likely from the supernova ejecta. And we have a Lorentzian component here, which is most likely due to interaction of the ejecta with the circumstellar medium. Now, Bielinski et al. Also did spectropolarimetric observation for this, and they found a depolarization occurring in the H alpha, and then it hinted towards the asymmetric distribution of the circumstellar medium. So when we have then I show you a case of a superluminous SN2N. So if you look into the absolute magnitude, you see that it's about minus 21 mag in the UV bands. It is about 2 mag brighter than the 2NP class of events. But when we move towards the spectral signature, they show like a normal standard 2N with narrow emission lines and intermediate with emission lines in their spectral profiles. So even if the luminosity is high, the spectral profiles are similar to a standard 2N here. Now, again, Bielinski performed spectropolarimetric observations for this, and we also tried to model H alpha, and we find that there is a narrow emission and an intermediate width component throughout the evolution. The polarization is very low for this event. So this is the one event which had very less asymmetry, or we would say more towards a spherical symmetric configuration. Now, so the question here is that when we say the structure is asymmetric, we have cases like 2014 AB on the top, and then we have cases like on the right, 2010 JL. So where we see Lorentzian profiles for a very long time. For this, for the 2014 AB, we see ejecta signatures, broad profiles for a very long time. So basically, it is the viewing angle which matters when you see a 2N kind of structure here. So if you look into a disk kind of circumstellar geometry like this, then if you are looking edge on, you would see ejecta signatures coming in. But if you look face on, then you would see the interaction of the ejecta with the disk. So it very much depends on the viewing angle and the geometry of the circumstellar medium on what lines we are seeing in the spectral profiles. Now, we have some cases of compact CSM. This has been talked about by various papers from the morning, but this is the one which had a compact circumstellar medium, and we could reproduce it with the inner CSM and an extended CSM configuration with mass loss rates of 10 to the power minus 2 to 10 to the power minus 4 M solar. And then it started to show normal ejecta signatures after a couple of days. So we have this compact CSM cases. And then we have this case of 1A CSM where we had radio detection, had NIR excess, and you can see narrow emission lines of helium in the spectral coming in by Eric Kuhl. And this was thought to be probably originating from a single degenerate binary system in which the white dwarf accretes material from a helium-rich donor star. So this is one and the only case, I think, of 1A which interacted with the nearby circumstellar medium. Now, if we move to 1BNs, so 1BNs are the one which show narrow emission lines of helium due to interaction with the helium-rich circumstellar medium. I show you a case of 2019 UO, which was the second 1BN detected with flash ionization signatures. And it was also the second 1BN after 2006 JC, which had a precursor detection. So basically, the progenitor star showed some precursor activity which could be detected in the archival images. And this is one of the few cases where we got progenitor precursor detection for this. If you look into the light curve, they are relatively short-lived light curves than 2Ns. And so along with 2019 UO, there is 2019 WEP as well, which showed this flash ionization signatures of helium, carbon, nitrogen due to recombination with a nearby circumstellar medium. So these were the very few events in which early on, which were detected as flash signatures for this class of event. Now, speaking of this class, 1BN are the group of events which are actually faster, which could be called as a subset of fast transients. So we know we have this 2018 cow-like events which rose fast and declined fast. And then we tried to plot some of our 1BNs on this comparison with the fast transient class. And we find that absolute magnitude wise, they are almost similar to the fast transients class, but decline wise, they are slow risers than fast transients, but typically a subset of that class, we can say. Now, Pellegrino et al. Showed this comparison of his 1BNs with 2018 cow, and he found that early on it showed this helium-2 emission lines like cow, and then the 1BN spectra profile changed over the evolution as time proceeded. Now, so we also tried to see the delta M15 and the absmac of this fast transients with this 1BN class. So here you can see that the rise times are larger than the fast transients group, but still when it rises early on, you can actually think that these are the fast transients members. If you look into the absolute magnitude scale, then we actually cannot find a correlation between them, but overall, these are higher luminosity members in general than a typical traditional core collapse supernovae. Now, when we have 1BN light curves, we try to model it with a circumstellar interaction model. So what we did here is that we tried to model it with a forward and a reverse shock composition, assuming the circumstellar medium is a both wind-like and shell-like configuration. And we tried to reproduce the light curves through modeling. And we find that for these two events, the CSM mass was in between 0.2 to 0.4 m-sun, and the radius of the CS circumstellar medium was in the order of 10 to the power 14 centimeters or so. Now, what is interesting here is that when you try to see the frequency of the 50, like the number of events, 1B events with this classes, then you see that 1Bs have higher 56 nickel masses and ejecta masses. And these are the events which have relatively very low contribution of nickel to the light curve. So they are mostly interaction dominated and have very less nickel mass contribution here. Now, for the ejecta masses, if you look into the ejecta mass, then they are, of course, lesser ejecta mass than the typical stripped envelope population, but still they are like, means the ejecta masses are still could be comparable to some of the 1Bs, but they are the nickel masses are relatively low for these group of events. So to summarize, this is a study being done by Hosseinzadeh et al. 2017, and he found that these are relatively bright members with absolute magnitudes always greater than -17 Mach. They are fast risers with a rise time typically less than 10 days, but they are slow, fast decliners as well. So after 30 days, the typical decline rate is 0.1 Mach per day. But if you look into the correlation between these parameters, he did not find any significant correlation between rise time, delta M15, or rise time decline rates. Now, he also studied the host galaxies of this group of supernovae, and he found that there is a strong UV emission, which implies the presence of massive stars, and we expect detection in bluer bands. So we assume that these are formed from star-forming galaxies. But then there is this case of PS112SK by Sanders et al. 2013, where they find that this has been forming in an elliptical cluster galaxy. So this is one event, unique event, which occurred in an elliptical galaxy. And they triggered HST for this. And then it was undetected, like no star formation was detected for this galaxy. So then the question arises now, like, is it like only the star forming galaxies contributing to the 1BN population, or these are there old elliptical galaxies also from which the 1BN population can come on? So the question here again is these classes are not distinct, and they are linked by a continuity of outer layers. So I present you a case of 2021 FOA, where you see that if you take the helium to H alpha luminosity ratio, this event initially matches the 2N population, then it lies intermediate between 2N and 1BN, and then it moves to the 2N population again. And when I plot the helium 1 luminosity to the H alpha luminosity contributing to the peak, this even lies kind of intermediate between the 2N and 1BN population. So there are events like this which actually bridges these two classes. Now, coming on to 1CM, these are a very, very new class where there are a handful of events, 10 to 15 as of now. And they show, so 2019 HGP was one of the paper by Abhishek Galyam, where he showed this narrow lines of carbon, oxygen, and neon, and no helium and hydrogen lines in the spectral profiles. And this is one from Pellegrino et al., where he shows that these are narrow P Cygni forming in the profiles of these group of supernovae. And their progenitors, of course, could be Wolf-Rayet stars, WC, WN kind of stars from which they arise, but they are so less in number that the progenitors are not explored yet much for this group of events. And then again, speaking of continuity, so this is the event 2023 XGO, which happened last year. And if you look into the +5T spectrum, you see helium-2 emission lines, carbon-3 emission lines there. And then if you move to the +7T spectrum, you see helium lines, narrow helium emission lines coming up in the spectral profile. So there are events like this in which we don't know like whether it is a 1BN with flash signatures from nearby circumstellar medium, or this is a 1CN which interacted with a detached helium shell later on, and then it started to show up narrow helium lines of helium emission lines. So we have these debated class also where we try to search like what is the continuity driving these two junctions or these two boundaries between 1BNs and 1CNs. Now we have some of the events like 2022 CRV here, where we see no interaction signatures in optical, but we do see radio signatures coming up in the spectral profile, which hints towards the existence of a circumstellar medium. And we try to model them with synchrotron self-absorption models and try to estimate the mass loss rates and radius. But for this case, we did not see any interaction signature in optical. So, and then when we finish these classes, we have these unique classes of 1C CSM kind of events where you see interaction signatures coming on at later stages. And then this is one of the work where we see narrow emission lines of magnesium and oxygen coming up from the circumstellar medium at later instances. So we have these cases as well, where we see a hydrogen-free, helium-free environment, but narrow emission lines of oxygen and magnesium coming up at later stages. So to summarize here, we see that 2N is a heterogeneous class. It is highly asymmetric. It could be from LBVs, but it could be from binary stars contributing to the light curve and spectral signatures. 1BNs are a relatively homogeneous class. The progenitors could be Wolf-Rayet stars, but they could be binary scenarios as well. Then the intermediate objects, which we see as the transitioning classes between 2 and 1BN, could be the one with LBV transitioning to Wolf-Rayet phases. The host galaxies are still complicated. It could come up at any point of time. And then 1CNs are the one where progenitors also we don't know. It's a relatively new class. We're trying to explore it more. So the questions to be addressed at this stage are asymmetries of the circumstellar medium and the ejecta, the viewing angle from which we see the circumstellar medium, the density of the circumstellar medium, the progenitor scenario, and how often the precursor activities or the progenitor activities are linked to this final supernova explosions. So there are many questions that need to be answered and dealt with more, and I would stop at this point. Thank you.
All right, thank you, Anjasha, for this overview. Questions?
Thank you very much. Very nice overview. I'm wondering about the 1CNs that you mentioned. Do you have any handle on the progenitor mass limits, so to say? Because there's one object that we know that looks like a Wolf-Rayet and it's helium-free, but that object is actually suspicious and considered to be a white dwarf merger. So I was wondering if this is a scenario that could be viable for these objects as well.
Yeah, I agree with you. So I think as of now, if we think of single stars, then we should consider that the ultra-massive stars which have stripped off enough envelopes, like ultra-massive Wolf-Rayet stars maybe. But of course, there are many binary scenarios which could actually contribute to this 1CN class of events. So Craig in his paper has described some of this scenarios of binary mergers which could give rise to these kind of stars. So of course, this could be a probable scenario where we could get like carbon or neon lines from the nearby circumstellar medium and binary giving rise to this. Yeah, thank you. Yeah.
Anyone else? Well, I could ask.
Can I ask a question?
What? Okay. Yeah, so I could ask a question. You had this slide where you had different types of, or different subclasses of type 2Ns, basically. And it's like way back in toward the beginning here. So I noticed that you are calling 98S a standard type 2N. Is this your opinion, or because it wouldn't be my opinion?
Okay, so I call it standard because I know 98S is the one which was considered to be not a long-lasting one, maybe because it dropped off quite quickly from the light curve and the spectral features as well. But I call it standard because these are the 1988Z and 80S were the prototypical members that we found early on to be classified as type 2Ns, and then we followed other events thereafter. So I call it as a standard one, but it is not a long-lasting one for sure.
Yeah, that's kind of what people tend to do with it. Yeah. All right, I guess we should move on to the next speaker, but let's thank Anjasha first. So the next speaker is Morgan Fraser from Dublin, and he's going to talk about gap transients.
Thank you. And thank you to the organizers for the opportunity to come and speak, and also to our local hosts for putting on a fantastic meeting. So I'm going to be continuing the theme of squeezing large classes of transients into a short amount of time. So to begin with, I just want to set the scene. So this is a plot originally from a paper by Kulkarni and Caswell, looking at a whole slew of transients in terms of how bright they are and how long they last. And if you start populating this diagram, you see all of the stuff that we've talked about and we've heard about so far this morning, normal core collapse, supernovae, interacting supernovae, the majority of them lie up here in the top half of the plot. If you were to go next door to one of the other sessions, you'd hear about galactic transients, so classical novae, stuff like that, and they lie down the bottom. What I'm going to talk about is what's termed the luminosity gap that lies between these. So this is an observation class of transients with absolute magnitudes brighter than the classical novae, things like that, so typically brighter than -10, but fainter than the supernova that we all know and love. So to start off with, this is an observation class. Let's take a spectrum of one and see what they look like. It turns out spectra can be fairly useless. Most of the luminosity gap transients, if you take a spectrum of them, look like this. You see something with a blue continuum, narrow Balmer lines, and often not a whole lot more. So really what you're seeing in this observation class of transients that are dominated by emission from circumstellar material that's being excited, that's being energized by what's happening in the middle. If you look at their light curves, suddenly they look very different. So this is a plot from a paper with Andrea Pastorello a couple of years ago, where we put together examples of some of the different subclasses of things that we see in the luminosity gap. And bear in mind, again, this is an observational class of transients. So we see things, many things with different physical natures, or what we believe are different physical natures within. And I'm going to go through these in turn. And keep in mind as well that this is not, and what I'm talking about today is not an exhaustive list. There's a lot more interesting stuff in the luminosity gap as well. And it's generally quite poorly explored because it's hard to find these things because they're quite faint at extragalactic distances. But let's take a trip through it. First thing we're going to look at are these guys up here, what are called luminous red novae. So we know that most massive stars are in binaries. So if you look, these are some statistics from surveys in the Magellan Clouds by Sana and his collaborators, and they find that basically every massive star is in a binary. These ones that are listed as effectively single, they're still in binaries, they're just really wide binaries. And if you look at the statistics, about a quarter of them are binaries that will merge over their lifetimes. So stellar mergers are actually common in massive stars. So what happens when two stars in a binary merge? Well, if you can imagine your picture of mass transfer in a binary where you have material being funneled through the Roche lobe onto a companion, and those stars get closer and closer, eventually you form a point where you have a common envelope around those two stars. Once you have that, the two cores of the stars are orbiting within this common envelope, and drag causes them to spiral in closer and closer, and either merge into a single star, or maybe you'll end up with a very tight binary afterwards. During this process, the common envelope that's formed around these stars will be ejected, giving rise to a luminous transient. We see examples of this in the Milky Way. This is probably the nicest example. This is from a plot by Telenda for V1309 SCO, where you see something over about 5 years. It's getting brighter and brighter and brighter by about a magnitude. This kind of scatter in the light curve is not photometric noise. Rather, this is because it's a binary. It's a photometric binary. And if you look at this and you look at the period of the binary, as time goes on, you find out that the period shown in this inset is actually decreasing with time. And as it approaches the point of merger, suddenly you see this big spike in the light curve, brightens by about 6 magnitudes, and fades away again. And afterwards, this periodicity, this flickering due to periodicity, is gone. We only have one star left. So this is in Milky Way. And we see things that are similar in other galaxies as luminosity gap transients. So again, this is a montage of a number of these luminous red novae. You can see the galactic examples, V1309 SCO and so on, that I just showed. Then here, they're quite faint, absolute mag -6. Can't find those in other galaxies. But if you look up here, slightly brighter cousins at kind of -12, -13, we see these luminous red novae. And they follow a very characteristic pattern. They're initially hot and blue, so dominated by narrow lines, and then they evolve to much cooler spectra. And then eventually, what we see that's left behind is a very cool, puffed up red star. So you see these spectra dominated by molecular bands. There's a lot of interesting things that are as yet unknown about these luminous red novae. If you compare the models, you find that many of the models are about a couple of orders of magnitude fainter than the luminous red nova we observe. They also happen to quickly. And there's a lot of open questions about what the geometry of these systems are. These are intrinsically non-spherically things. You have two stars spiraling into each other. And there have also been suggestions that at least in some instances, these mergers can trigger core collapse supernovae. Okay, luminous red novae. Let's look at some of the other stuff that happens in the luminosity gap. So people have already mentioned supernova imposters, LBV outbursts in brief. Let's look at these a little bit more. So again, turning to our own galaxy as a template, if you will. The kind of classical supernova imposter that people look to is Eta Car. So this is a star. It was a completely unremarkable star to the naked eye about 150 years ago, and then suddenly it brightens by about 5 magnitudes. And when we look at it now, this is an image from the Hubble Space Telescope, you see that what happened a century and a half ago was that this was a star on the order of 100 solar masses, 150 solar masses, that ejected about 10 solar masses of material from its envelope. We don't know the physical mechanism behind this. Probably or potentially something connected to a close periastron passage of a binary companion. But what is important for us is that if you were to put this in another galaxy, it's a supernova imposter. You would see something with a hot spectrum, narrow lines, absolute mag about -13. And lo and behold, we see things that look like this in other galaxies. Again, you've seen 2009 IP mentioned as a type 2N supernova, but before it was a type 2N supernova, it was a supernova imposter. So this is a series of spectra taken after it was first discovered, having one of these eruptions. You see here in the light curve reached about -13, so similar to Eta Car. Again, you see the characteristic narrow Balmer lines of low velocity circumstellar material. Don't know what triggers these. Don't know what powers them. They're not terribly common. But again, we're observationally very incomplete. This was found at about 20 megaparsec. If you put it a little bit further away, you're gonna miss it. What's really exciting about these LBV eruptions is that in some instances, if we look over here, they appear to presage a genuine core collapse supernova explosion. So this is really something that a star is doing just a few years before it explodes. So if we go back to this plot and we're extending it out a little bit more in time, this is kind of the 3 years of being a supernova imposter, and then suddenly it brightens to about -18. And we think now that this was the core collapse of a massive star that was experiencing this eruptive mass loss in the final couple of years of its life. Over the past number of years, there's been a bit of discussion as to whether this was actually a genuine supernova. After all, they've got this massive star having outbursts and eruptions. Maybe this really bright thing is actually powered by just collisions of successive shells of material that was lost by the star. Just in the last year or two, though, I think this has been fairly conclusively settled, thanks to HST imaging. So you can see here an example of another one of these events. This is 2016 JBU, and in a nice paper 2 years ago, Sean Brennan showed that if you look at the progenitor, you see the progenitor beforehand. This is before it was a supernova imposter even, and you go back and you look afterwards. Basically, that luminous massive star has gone. There's a little bit of residual flux there, but that's just lingering supernova emission. And If you really, really don't want to believe the star exploded, you could say, well, maybe it was just enshrouded by dust. And he thought of that as well. So what you see here, this is again the pre-explosion photometry. It's positioned on a HR diagram. Incidentally, not a very massive star, 22, 25 solar masses. So lower mass stars can experience LBV-like phenomena as well. But if you put an arbitrary amount of dust on that star, you can hide it. The problem is you'd need to find a lot of dust. You'd need to form about 1/10 of a solar mass of dust in a couple of years without changing the color of the transient and without actually having any metals to form that dust out of. So that doesn't work. So some stars really do have big outbursts just before they explode. And this is, again, consistent with what you see from follow-up observations of supernova that a lot of people have mentioned in the morning session, that you see evidence for confined CSM close into stars. Again, physical mechanisms for these eruptions immediately prior to a supernova explosion are unknown. There have been a large number of suggestions. But from the timing, again, these things are happening sort of order a couple of years before collapse. You're looking potentially at something associated with oxygen burning, maybe shell carbon burning, if it's some instability associated with the final years of a star's life. Okay, so we've talked about luminous red novae, we've talked about LBV outbursts, pre-supernova eruptions. What else is in the luminosity gap? But the last thing I want to talk about are these guys up here. Sort of weak supernovae, failed supernovae, ilerts. So again, plotting a set of light curves for a subset of our luminosity gap transients known as ilerts. We see a set of them that are absolute mags sort of -12, -13. And if you were to ignore the numbers on the axes here, you might kind of squint your eyes and go, this looks a bit like a type 2 supernova. You've got someone who's got a bit of a plateau and then it fades away and there's a tail. The problem is when you look at the numbers on it, you see that these are much, much fainter. The tail phase, if that's what it is consistent with, a few thousandths of a solar mass of nickel. So really small nickel masses. And again, this plateau is dominated by narrow emission lines. So most of what you're seeing is actually circumstellar material around the star rather than the ejecta itself. There's a suggestion about a decade and a half ago now by Maria Teresa Botticella that these events were electron capture supernovae in low mass super AGB stars. So these stars about 8 solar masses. This is also supported by the fact that in a couple of cases as progenitors, and we've seen really dusty, low mass stars that seem to disappear after the supernova fades away. I want to show one interesting result in this though that did quite recently. So this is work by Robert Byrne, where he looked for a sample of these ilerts, looked at the strength of sodium absorption seen in their spectra over time. And what he sees is actually the strength of the sodium line varies over time. And this is just one example for NGC 300 OT, but we've got half a dozen other ones in his paper you can look at, and they all look different. Some of them go up and down, some of them go down and then up, some of them stay constant. And what we think is causing the change in sodium line are two competing effects. One is sodium in the absorption in the circumstellar material being swept up by supernova ejecta. On the other hand, you have photoionization of sodium to sodium 2 by UV photons from interaction. And what the cause of the diversity of evolution in sodium lines that you see actually reflects the diverse density profile and the complex density profile you see in CSM. So again, this is consistent with what other people have mentioned this morning, that when you look at CSM around massive stars and CSM around supernovae, it's probably not a smooth R to the -2 wind. So as we've seen from radio as well, and other evidences, it's probably something that's quite complex, it's quite structured. Final thing that kind of lies in this luminosity gap, and I just want to flag up. So Beth Fitzpatrick will be talking about this in a talk in a few moments. Is whether we see failed supernovae in this region. So it's kind of a long-standing suggestion that actually some massive stars, some of our 20 solar mass red supergiants, don't explode as a core collapse supernova. Rather, they collapse, they don't rebound to form a successful explosion, and it collapses down to a black hole, and you get a very weak transient. There's some observational evidence for this. Possibly now, this evidence is getting a little bit weaker as we're seeing more and more dust enshrouded red supergiants. But on the other hand, there's also theoretical support to this. So people that do modeling of sets of progenitor models find that there's actually islands of explodability and islands where stuff doesn't explode. So why I'm mentioning this and why this is relevant to talking gap transients is if you have one of these failed supernovae, you would also expect to see it as a gap transient. The reason is that you lose about 0.1 solar masses to neutrinos when the star collapses, and that drives a weak shock into the rest of the star, into the envelope, as the star adjusts. And remember, red supergiants, their envelope is very loosely, tenuously bound, so even a weak shock can still eject a little bit of the envelope, and you get a really weak, dim transient lasting several hundred days. So this is some models from Lovegrove and Woosley that show what this would look like. We had a paper last year where we actually conducted a search looking for these failed supernova outbursts using archival ZTF and PTF data. We didn't find any. We found a whole bunch of weird transients. We don't know what they are. So things like, a 30 solar mass yellow supergiant suddenly fades by a magnitude and brightens by a magnitude. Don't know what causes that. Our limits for failed supernova from extant data are, there's probably a kind of 50-50 chance we would have seen one. So we'd have to be lucky. But when you get to the forthcoming Rubin, you will definitely see them. And this is what I want to finish up with. So everything I've shown you so far is really what is just scraping the limits of detectability with the existing surveys. If you have ZTF, Atlas, Assassin, Pan-STARRS, go to your survey of choice. They all go down to about 20th magnitude, give or take. That means if you're looking for luminosity gap transients, if you're looking for someone that's minus 12, you can detect it at 25 megaparsec. A little bit brighter, you can find it a little bit further. With Rubin, with these things, you can detect the same transient out at 150 megaparsec. So that's 200 times the volume that you can survey. So I think really over the coming 2 years, we should expect a whole slew of these things. We've just scraped the surface of what's detectable and what's doable and what we can find and study. And there's going to be a lot more to come. So that is it. Thank you. And I'd be happy to take any questions.
Okay, any questions for Morgan? I've seen a few hands, but yours is the one I saw first, so.
Hey Morgan, nice talk. With the supernovae, well, not the supernovae, but the imposter that you had the HST imaging for, have you checked whether James Webb's observed this field yet? Because that would be great for your dust argument or not.
Yeah, no, we have F160 observations with HST, which is as rare as it goes. None of them have been observed with GWST yet. I don't know if anyone's applied to, but I think it's honestly, I think at this point, dust, there's a very small bit of parameter space where you can explain it with dust. I'm not even sure if it's worth hitting it with GWST to rule out. I'm pretty comfortable with it, but it would be nice to go back and see. Sooner or later, one of them is going to happen in a galaxy where it's observed by GWST for another purpose, and then we'll get it.
We got time for one more quick one, but I think yours is the one I saw next. So.
Hey, nice talk. For Rubin, I mean, yeah, we'll see a lot of stuff, but it doesn't have a great cadence for these things. So, like, how many will we be able to do something with?
This is the question, I guess, and it's not just gap transients, right? Most of the stuff that Rubin finds is going to be too faint to get a spectrum of. That's going to be the bottleneck. I would say for some of the gap transients, the fact that Rubin doesn't have a great cadence is probably not terrible. Like if you look at a luminous red novae, you know, there can be a couple of 100 days. Failed supernovae, you know, a year, something like that. So Rubin's quite good. The fast stuff, the LBV outbursts, things like that, where it could be, you know, flicking on and off in a week or so. Yeah, we're going to struggle there. Yeah, I agree.
Okay, one more very quick one.
So I have a question about the Red Supergen program. So now that we got 23 IXF and then, you know, people don't agree on the initial mass. So how much do you trust? Like, is the problem real?
I mean, I can't answer that question about whose mass I believe without offending at least somebody in this room, right? Okay, what makes me a little bit worried is that we have a whole bunch of kind of limits, non-detections, detections, where it's consistently below 16 solar masses. And in the last couple of years, we start finding ones where we have good infrared data. The ones with the best data have the highest masses, which makes me a little bit nervous. In terms of progenitor observations, it's tricky. I think Emma Baser and people like that have said this for years, that you could actually have these things enshrouded by dust. The one thing I would like kind of maybe gives me a bit more confidence in it is that you also have to explain the nebular spectra. So there's nice work by people like Anders Yerkstrand where they show that if you have a 20 solar mass star blowing up, you produce a solar mass of oxygen. Now, I know it's possible to suppress the oxygen lines depending on how you do the mixing. So if you can mix stuff down into the silicon burning layer and stuff like that, you can get weaker oxygen lines. Honestly, I'm not the best person to comment on that. But I think it is kind of encouraging that in that instant, at least nebular spectroscopy and progenitor detections do agree. But if we find a dozen more with data like IXF and 24 GGI, then we can solve it. And we will.
All right, we need to move on now. So our next speaker is, oh yeah, let's obviously thank him again. Sorry about that. But yeah, our next speaker is Takatoshi Ko from Tokyo and talking again about interacting supernovae.
So thank you for introduction. I'm Takatoshi Ko from University of Tokyo, Japan. And today I will talk about a binary population synthesis study on type 1b and supernovae. And they are my co-worker. Oh, thank you. So as you have heard a lot today, thanks to recent developing observation techniques, there are many supernovae with narrow line have been discovered, and there are so-called interaction supernovae, and those with hydrogen narrow line is so-called type 2N, and those without hydrogen but with helium narrow line is so-called type 1bn supernovae. And these narrow lines are thought to be caused by some interaction between supernova ejecta and the surrounding dense CSM. And then what makes this dense CSM? So for ordinary stellar winds, the mass loss rate is about 10 to -4 solar mass per year, but this value is not enough at all to explain the required CSM to cause type 2N or type 1bn supernovae. So some eruptive mass loss scenario is required to explain this high mass loss rate. And in single star scenario, some scenario is suggested, like nuclear burning instability, potential instability, core neutron radiation, and so on. But this single star eruptive mass loss scenario is thought to be possible for type 2N supernovae. However, for type 1bn supernovae, it is difficult to explain the eruptive mass loss by this single star scenario because the helium star, the 1BN progenitor is thought to be a helium star, and helium star is much more compact than the hydrogen red giant or hydrogen red supergiant. So helium star, helium CSM is very difficult to be formed by a single helium star. So that's why we think this type 1BN supernovae are binary, maybe it's binary origin. And also for the normal type 1BC supernovae are thought to be maybe binary origin. Because in order to make such helium star as a progenitor helium star or carbon star, it's difficult to make them by single star evolution. So they are thought to be binary origin. So in that sense, type 1BN supernovae are also maybe binary origin. So if type 1BN supernovae are binary origin, we can estimate the event rate by population synthesis calculation. So in this work, we estimate the type 1BN supernova event rate and compare the rate with the observational rate. So this is the setup. We adopt Harmonic code to do the population synthesis, and we set the binary parameter alpha lambda equal 10 to -2 to 10 to 2, and beta as a mass loss rate in a stable mass transfer binary 0.1 and 1. And in this work, we set the beta equal 1 is no mass loss from the binary system. So we prepare 10 to 6 binary systems for each parameter set, and we set the initial mass 3 to 100 solar mass randomly based on initial mass function. And we think in order to cause type 1BN supernova in binary, enough mass loss is needed to cause dense helium CSM. And also, in order to cause type 1BN supernova should be occurred as soon as the CSM formation. So at least less than a few years. So we extract some evolution scenarios, type 1BN supernovae, which satisfy these conditions. So here we consider two scenarios. One is T0-like scenario, and the other is stable mass transfer scenario. So for the first one, we consider the T0-like scenario. The T0 object is a red giant with a neutron star in center. So it means a neutron star exists in the red giant center. So in this scenario, we consider two helium star and neutron star binary system, and it makes a common envelope. And in the common envelope evolution, the core and the neutron star collide. And we think at the time, the neutron star goes into the helium core, and it actually accelerates the stellar evolution. And as soon as it collides, it makes an explosion. So in this common envelope evolution, it can make such a high dense helium CSM. So we think it can cause type 1BN supernovae, and we assume the all binary system like this can occur type 1BN supernovae. So, and the other one is stable mass transfer scenario, and here it's easier scenario, and we think stable mass transfer from helium star to neutron star. And under this condition, if the helium star explodes, we think this can be a type 1BN supernovae. Of course, not all can be a type 1BN supernova because it depends on the explosion timing and when the CSM is formed. But here we count the all system is type 1BN. So in this sense, we overestimate the type 1BN supernova rate in this calculation. So this is event rate. The observed event rate is 1% to normal core corpse supernovae, and we count type 1BN supernovae in each parameter set and CCSM for each parameter set, and then we can estimate the ratio, type 1b ratio to CCSN. So this is the result. So observed ratio is 1%, but our estimate, our calculation shows it cannot, a neutron star and helium star binary system cannot explain the observed rate at all. So the maximum one is 0.2% to the CCSN. So neutron star helium star binary cannot explain the ratio. So discussion. So we find neutron star and helium star binary cannot explain the observed supernova type 1b and supernova numbers. So there can be other possible evolution. Of course, single star evolution maybe the case, but we think the helium star explosion in main sequence and helium star binary can be the case. So because in recent Samantha's work, she reported in some specific low mass helium star, extreme mass loss can be occurred. So if such helium star with specific mass and main sequence binary, in such binary system, if helium star explodes, it can be a type 1b and supernovae. But yeah, this kind of population synthesis calculation is needed in the future work. And that's it. Thank you.
Thank you. Questions for Takatoshi? All right.
A nice talk. I was wondering, what is the basis of considering the TZO-like scenario? Like, do you have any previous idea or previous paper which made you think that this could be?
In Chevalier 2012, they suppose that type 2N supernova can be occurred via such common envelope evolution and TZO like something. So yes, that's why we think this can occur.
But that was a hydrogen-rich one. Okay.
Yes.
Okay. Thank you.
Unfortunately, we don't really have time for more questions, so let's thank him again. And the next speaker we have, and I'm going to give this a try, Moshgan Agakhanlu. Okay, good. Yes, I'll give you this mic. But she's from the University of Virginia and will talk to us about supernova imposter outbursts.
Thank you. Okay, so today I'm going to talk about a supernova periodic outburst of a supernova imposter, 2016 BLU. And in the right side, you can see, in the right side here, you can see 16 BLU during one of its supernova imposter outbursts captured using a Kuiper telescope in 2018. So a quick background, supernova imposters, they are evolved massive stars that they experience a bunch of non-terminal eruptions. And they are usually misclassified as supernova explosion, but later, since the star survives the eruption, they are labeled as supernova imposters. And their eruptions are often interpreted as giant eruptions of luminous blue variables or LBVs. And in the right side, you can see the HR diagram where luminous blue variable is a phase, post-main sequence phase of massive stars, where a very massive star becomes unstable and variable. So we were lucky that 16 BLU's galaxy was monitored by Kate telescope. So here we have the light curve from 1998 to 2009. And the gray bands that you see in this light curve is the time that when it's hard to observe 16 BLU because of its vicinity to sun. And as you can see, is a stable system till 2009. And then in 2012 experienced its first eruption. And I should mention that in today's talk, I'm going to use eruption and outbursts interchangeably. So here we have its life curve from 2012 to 2023. And we have data from telescopes in Arizona, like Kuiper, Superluminous, and also we have data from ZTF, Atlas, and also this is the first supernova imposter detected by Gaia. So using all these data, we found that 16 BLU experienced at least 19 outbursts from 2012 to 2023. In the top left, you can see its first outburst in 2012, and then you can see 3 more selected outbursts in 2019 and 2020. And as you can see, during each event, there are multiple narrow peaks with similar magnitudes. 2 of these outbursts are also detected in infrared. In light red and blue, you can see its Spitzer data, and we found that 16 BLU also experienced 1 outburst in 2014 and another one in 2016. We found that these outbursts, they do repeat with a period of around 113 days. Here we have the Lom-Scargill periodogram, and as you can see, there is a dominant peak around 113 days, but there's another peak around 38 days, which associated with the multiple peaks that we are seeing because they are approximately 30 to 50 days apart from each other. Here we have the same light curve that I showed at the beginning of the talk, and the red vertical dashed lines show the estimated time of the outburst using the period of around 113 days. And as you can see, most of the peaks, they align pretty well, so the period is not changing that much. So in the paper, using the period of 113 days, we proposed the time of upcoming outburst. And this group, they observed it around the same time that we proposed, and they confirmed that 16 BLU experiences 20th outburst. Then we started an AAVSO observing campaign, and with the help of approximately 13 amateur astronomers, we confirmed that it experiences 21st outburst around the same time that we proposed. And in the left side, you can see 2 of the images taken by amateur astronomers. So since this is a periodic outburst, we propose that this is an eccentric binary system where the primary star is a luminous blue variable. And these outbursts that we see, they are caused by interaction between 2 stars. So in part A of this figure, you see when the primary star is as its quiescent state, so the interaction between 2 stars during periastron encounters is weak or even absent. And in part B is where the primary stars experience an LBV variability, so the interaction between 2 stars during periastron encounters is much stronger. So every 113 days, we may not see an outburst because of the LBV variability. And these interactions, they can be, for example, wind-wind collision or accretion into a compact object, depending on the nature of the companion. So this is a target of great interest because these periastron encounters, they look very similar to the periastron encounters in Eta Car leading to this giant eruption. You can see Eta Car's light curve in the top right. And then also they look very similar to pre-supernova eruptions of supernova 2009 IP that you can see is light curve in the bottom right. And supernova 2009 IP is the first direct link showing that LBVs, they can be direct progenitors of supernova, opposite of what theoretical models propose. So we encourage to monitor 16 BLU because it may experience a giant eruption or it may become a supernova. So we have done much more in this paper, and unfortunately I don't have time to go over all of them in details, but quickly I would like to mention that we compared the spectra to supernova 2009 IP, showing that they're very similar. Also using HSC archival images, we estimated that it's at least 33 solar mass star, most likely even more massive than that, and we compared it with other LBVs. Also, since we are seeing multiple narrow peaks, and also we are seeing excess IR, we propose that most likely there are dust shells around this system similar to WR140. So in summary, we showed that using optical and infrared data, 16 BLU experienced at least 19 outbursts between 2012 to 2022, and 2 of these outbursts are detected in infrared. We also found that these outbursts, they do repeat with a period of around 113 days, and we propose that these outbursts, they are caused by interaction between 2 stars in an eccentric binary system where the primary star is a luminous blue variable. And if you're interested to learn more about this target, I encourage you to look at the paper using the QR code. Thank you.
Use that mic. Okay, questions? There are a couple. Let's start with you.
Thank you for the talk. I might have missed it, but what was the mechanism that turned on the periodic outbursts? Because it was not detected before, right?
Oh, you mean the first one?
Yeah.
Okay, so in general, we think these outbursts are because of the interaction between 2 stars, like wind-wind collision or accretion into the compact object. What it caused, the one in 2012 that we didn't see it before, the short answer is that we don't know. The longer answer is that if you look at the light curve that I showed, it may take a while I go back, but specifically using Gaia data, we see that it was brightening over time. So we think that maybe because the primary star is expanding, that expansion started the interaction between 2 stars.
Thank you.
Did that answer your question as well?
I also asked about the secular increase in brightness.
Yeah.
Oh, sorry.
I think there was one before you, I think.
Thank you. Sorry if I missed it, but given the what's the distance? Is there any chance to get reasonable spectra of this object, maybe on and off outburst?
Yes. So the distance is around 8 megaparsec, but we have a lot of spectra that is a work in progress. Hopefully, the paper is going to be out soon. We have a lot of data from various telescopes.
Okay. Do you have a quick question?
I was wondering, like, we have many 2Ns or 1BNs which have precursor activities going on. So how do you distinguish these events actually when you see early on observations?
You mean distinguish in what terms, like LBV wise?
Yeah.
So the thing is that when we say LBV is a bag of 20 or I don't know, a number of different type of stars. So in my opinion, when we say LBVs, it's just a non-supernova explosion. But we need more data and studying more well to really distinguish them. Right now, I don't think we are really. So whatever is not a supernova explosion, maybe like that.
Okay, let's thank Moshkan again. Next up, we have Thomas Moore from Belfast, and he's going to talk about this weird type 1c supernova.
Okay, thank you, everybody. Thank you to the local organizing committee and the scientific organizing committee for the opportunity to give this talk. I thought until quite recently it would be a poster, so it's a thrill to actually be able to come and present here today. I'm a PhD student in the transients group in Queen's Belfast, and for the time being, I'm lucky enough to be a, oh, sorry, can I move this up? Sorry, yeah, can you hear me okay? Yeah, I'm fortunate to be a student in ESO Chile. I'm talking about this supernova that is, I think, a very interesting type 1c. These are results from an AppJ letter we published late last year, and there's some remarkable observables that I'll discuss. I would like to start the discussion of the supernova by highlighting the discovery. It's been a bit of a running theme for this meeting, the notable contributions to our field from amateur astronomers, and indeed the supernova is no different. 2022 JLI was discovered very nearby at the Clancarry Observatory by the notable supernova hunter Berter Monard. in this beautiful NGC 157 galaxy with a pretty uncertain host galaxy distance estimates, and we assume a 23 megaparsec distance. The supernova was discovered just emerging from solar conjunction. So unfortunately, we don't have pre-explosion non-detections to constrain the light curve, but we have a very full first observing season data set. Going one better, actually, the amateur astronomers of the polar supernova hunters classified the supernova, which is extremely rare in this day and age of professional supernova surveys. The spectroscopy that we've gathered shows a type 1c supernova, relying on Daiichi's very nice review to introduce type 1c supernovae, but essentially they're hydrogen and helium per. This particular supernova shows strong sodium D lines, silicon lines, and also very strong iron P Cygni lines that we use as tracers of the photospheric velocities. We see, rather unusually, that minus 39 days before what we call the main peak of the supernova, the velocity is 8,500 kilometers per second, but actually the recession of this photosphere inside of the ejecta is remarkably slow for a type 1c supernova, which we take as evidence of a large ejecta mass. We also note the rather unusual emergence of H alpha in the late time spectrum, which I'll discuss slightly more later on. We also constructed a TARDIS model with a plausible type 1c composition to see if with a synthetic Monte Carlo radiative transfer code we could reproduce the observables of the supernova. And indeed, I think we can. Photometrically, we collected quite a remarkable data set, I think, combining data from a lot of different facilities. And in fact, many facilities and data points were omitted from this plot, so we can actually see the light curve and see what's going on. Notably, though, we have very good light curve coverage from ATLAS, ZTF, photometry via laser. And I think looking at this plot, it's kind of funny. You can figure out when the supernova community realized this was a very interesting supernova because all of the multicolor follow-up started. But I would like to highlight three features of the supernova that are remarkable, and I think any one of them would be subject of a paper by itself. The first one is the rise time. So after discovery, quite a few of the annotations on this plot aren't showing, sorry, but just after discovery, where the left-hand side of this green marker is, there's a dip and then a rise. So the rise to maximum light is at least 59 days. Like I said, it's unconstrained because we don't have pre-explosion non-detections. The early access is something quite remarkable, 25 days. This is remarkable for type 1c supernovae. There's only a handful of supernovae where we see this, and they belong to this interesting family of interacting type 1cs. And then these periodic bumps, which is a unique feature of the supernova and will be the main focus of this talk. But just briefly to try and explain the rise time, here I have constructed a bolometric light curve from the photometry from the slide before, and I'm comparing it against a handful of type 1c and 1b supernovae, some of them which do show double peaks. I think 22 JLI resembles a little bit IPTF 15 DTG shown here in the orange, but it's a much more extreme example with a much more extreme early access, longer rise to peak, but a similar late phase evolution. When we compare the peak luminosity of the supernova to the recent Prentice et al. Compilation, we see it's within roughly the reasonable luminosity range. But the rise time is extraordinary. And we attribute this to a large ejecta mass to give us the photon diffusion time to reach maximum light at least 59 days after explosion. Here I show an Arnett fit, although we also compute a MOSFET model, and we need somewhere in the range of 5 solar masses of ejecta material. The early access, we don't actually discuss it too much in the paper because we don't have a good model for it. But the CSM interaction model we rule out because we require over 20 solar masses of CSM to be sitting near the star to give us this long duration kind of shock cooling-esque or just detached CSM interaction duration, which is I think is not physical, and we rule that out. But we do adopt something from the 1A community, and we use the Kaysen 2010 model for companion star ejecta interaction. This assumes a radius and separation, but we think that it's just a good energetics example. So we consider this as a plausible explanation, but it does have a viewing angle effect. But now coming to the periodic bumps, yeah, there's some lines missing from this plot, but what I've done here is I've just detrended the post-peak light curves and then plotted them. There should be a very nice, pretty sinusoid to guide the eye here, but unfortunately that's not present. If we go back. So you can see here, maybe by eye, above and below 0, you can see a rise and fall, rise and fall, rise and fall in the detrended light curves. This is not noise, it's not a coincidence, and I think we've verified the signal. We did this by doing something very similar to the previous talk. We use a Lumskargel periodogram in all the bands where we have very nice 200-day supernova decline. Here in the B band, the G band, the C band, this 12.5-day period is present and significant. To rule out a instrumental or a systematic effect, thank you very much, we calculate the Lumskargel periodogram for bespoke telescope and band combinations, and then feeling very confident, we phase folded and made the first phase folded supernova light curve. We consider two mechanisms. One is a compact object accretion scenario, the other a colliding wind binary. They both have their problems. The problem here is the diffusion from a central power source, and then in a colliding wind binary scenario, it's light travel time between shells. Both have the same effect of broadening the signal and making it less distinct. So we weren't the only paper to publish on this source. These are results from Chen et al. 2024, which shows that the H-alpha line intensity I mentioned earlier actually tracks the increase in the bolometric luminosity. And then on the other panel, on side B, the same point colors are used, showing an H-alpha line shift. And I think this closes the book in the colliding wind binary scenario and means that we're actually seeing a surviving neutron star and hydrogen-rich star binary post-supernova explosion. So I'll just finish now. I'm running out of time, but here's a very nice schematic from an ESO press release and my conclusions. So we think this is the first time we've seen clear evidence that, at least in the supernova, that the binary has survived and has interacted post-supernova explosion. This is part of the family tree of double neutron star systems and high mass X-ray binaries, etc., and ultra-strip supernovae. And I'll end there. Thank you very much.
All right, questions? So your hand shoot up immediately.
Oh, just a quick comment suggestion. What I would do to demonstrate your veracity of your period from those images, just do exactly the same analysis on comparable stars in the fields of Atlas and whatever. That's quite trivial. And I saw you had a Podolsky reference in there.
Yes,
because, as someone who works on the HMXBs and so on, this is exactly the kind of thing you expect. We know they survive the
yes, we do
I
know
think
that.
this looks really interesting.
Yeah, thank you very much.
Do either of those models give some account for why such modulations might be observed so rarely? Would it have to do with viewing angle or something just working in your favor to make these
so I think
stand out?
Yeah, in 10% of cases, you expect the binary to survive, so that rules out 90% already. Yeah. And then in this scenario, we need some mass to be transferred from the companion to the newly born neutron star compact object. And I don't have the numbers to tell you how often that happens, but observationally, it must be intrinsically very rare since we have never seen anything like this before.
All right, let's thank Thomas again. And we got one more speaker left before the poster session, so let's get to it. We have Beth Fitzpatrick from Dublin, and we will return to the subject of gap transients.
And so hi, my name is Beth Fitzpatrick, and I'm doing my PhD in University College Dublin. And you already heard from my supervisor, Morgan Fraser, earlier in the session, but I'm going to be talking to you about luminosity gap transients and more specifically AT 2019 KRL. So you've already heard a good bit about gap transients already, which makes my job a good bit easier. But just as a quick summary, we've plotted here a lot of the different types of transients, which we've put into observational groups. So we have the luminosity on the y-axis and the duration on the x-axis. And the luminosity gap transients fall about here. So in that luminosity gap between core collapse supernovae and classical novae, so hence their name. And there are many different types of luminosity gap transients. So we have the ILRTs, they're intermediate luminosity red transients, LBV eruptions, luminous red novae, and also failed supernovae. And each of these gap transients has a different causal mechanism, but they all result in about 1 to the power of 49 erg of energy being released in a really short space of time. And as a result, they observationally look very similar, and that makes our job in trying to differentiate between them really difficult. And I'm going to talk now about the particular gap transient I've been studying. So it has the name AT 2019 KRL, and it exploded in 2019 in M74, so about 10 megaparsec away. And immediately after this gap transient exploded, it was classified as either a type 2N supernova, which is an interacting supernova, or an LBV. And it was later studied by Jennifer Andrews, who favored this LBV scenario. But unfortunately, she had a really limited set of data. So there was actually only a handful of observations post-explosion, and they missed the peak entirely in the optical. So as a result, this made this really difficult for them to actually classify the transient, and their spectra and light curve were consistent with many of the different types of gap transients. So my goal then was to reanalyze this gap transient with a much more comprehensive set of both optical and near-infrared imaging and spectroscopy. So the first thing I did was to perform photometry on 19 KRL, and this is the light curve that I got. So it is the black curve here, and that is the OR band, OR band absolute magnitude. And I've plotted it alongside some of the OR band absolute magnitude light curves of the other gap transients. And this is a bit of a noisy light curve, and we can't really constrain too much from this, but we can see that it doesn't have this double peak that we see in this green light curve. That's characteristic of luminous red novae. As well as this, it's quite a flat light curve. It's definitely not, it's definitely a lot flatter than this red ILRT light curve. But I think the main take-home message of this is how dim the gap transient is. So its peak OR band magnitude is -10, which is significantly fainter than these other gap transients. And that is quite an important result that I'm going to come back to. But first, I want to look at the spectra. So we got 3 spectra of 19 KRL. So 8 days after explosion, 20 days after explosion, and another one 69 days after explosion. And all 3 spectra are quite flat and featureless, with the exception, with the exception of this strong H alpha line that is prominent in all 3 epochs. And this line doesn't weaken with time, which is quite significant, because if this was a luminous red nova, we would expect it to weaken. Actually, if this was a luminous red nova, we would expect the spectrum to evolve to become similar to an M or a K type star at late times. And we don't see that here with 19 KRL. So in this 69-day spectrum, we don't see any molecular absorption lines that are characteristic of M or K type stars. So we can kind of rule out a luminous red nova as a progenitor here, but we're still left with the question of what was the progenitor, because there's still a few different scenarios. And we've plotted here the spectrum of 19 KRL alongside some examples of the other gap transients. And it looks quite similar to a few of them, but it most resembles this yellow one here. So that's an LBV spectrum. So when we combine both the photometry and the spectroscopy, it so far looks most like an LBV. But we need to remember that failed supernovae aren't included in any of these plots, not the light curve or the spectra, because there are no confirmed observations of these, so we have nothing to plot. So that is another possibility that we can't forget about. So we were quite lucky with 19 KRL that we got a lot of images, both pre and post explosion with HST. And it was the final image that was taken in August 2021 that was particularly important. And in that image, KRL appeared to fade significantly. It actually faded to below its progenitor level. And before I go on to talk about why that was so such an important and unusual result, we first want to test the genuineness of that image. So 19 KRL wasn't the target in that image, and it was just kind of luckily caught in the field of view. But unfortunately for us, it was right on the edge of the chip. So if you look on this, this is the late time August 2021 image, 19 KRL is right on the chip edge. And as a result, we kind of need to question whether we can trust this image. So what I did was I performed photometry on all of the sources that were near that chip edge in that August 2021 image. So I took all of the sources within 3 pixels of this chip edge, and I plotted them here in red. So the y-axis here is the F814W magnitude from that image, 2021 image, minus its magnitude in a reference 2019 image. And in general, these sources are all clustered around 0 on the y-axis, which is a good indication that these 2 images are consistent with each other. So there are a few obvious outliers here. So this one in particular, that is a cosmic ray. And then there's another couple of outliers which we think are due to errors in the cross matching. But in general, the 2 images are consistent. We then repeated that for sources that were far from the chip edge. So I chose a region between 50 and 100 pixels and repeated the same analysis. And that's all of the sources in gray here. And I got similar results for that. And then finally, I repeated that for 19 KRL, and that's that gray point. And you can see that that is clearly an outlier. So that is a good indication to us that the proximity of 19 KRL to the chip edge is not the cause of the dimming, and that the dimming of 19 KRL is genuine. But then what does that mean? So if we look at the light curve of 19 KRL, then it started out at this progenitor magnitude, underwent its explosion where it brightened a lot. It then faded back to its progenitor magnitude, but then it kept fading and it became about 2 magnitudes dimmer than it was pre-explosion. So that is telling us that this then must be a terminal explosion or a genuine supernova. But if you remember the light curve from 19 KRL, its peak Orban magnitude was -10. So that's extremely faint. It would actually be the faintest core collapse supernova ever discovered. And really the only way we can get a supernova that faint is if it is a failed or a fallback supernova. And these are supernovae that directly collapse to, or they have progenitors that are very massive stars, and they directly collapse to a black hole, and they swallow a lot of the ejecta as they do so. And as a result, instead of a big bright supernova explosion, you just get this dim transient. So there are no confirmed observation of fallback supernovae, which is then makes this result extremely important, as 19 KRL could be our first confirmed observation. But before I get too carried away with that, we need to okay, that didn't come out. Yeah, we need to consider the fact that this could be an LBV that's been enshrouded by dust that was emitted when the explosion occurred. So I ran some dusty models using the Phoenix models, and then used PySynfot to calculate the synthetic magnitudes for F555W, F435W, and F814W magnitudes. And any model that was consistent with the color within 0.05 mag, I plotted the properties of it. And you can't see it here, but I can show it to anyone who's interested afterwards. It was a particular panel that showed the luminosity and the effective temperature that was particularly important here. And it showed us that between the progenitor, and it showed us that there were models that were consistent with 19 KRL becoming fainter than its progenitor. But for this to be the case, it had to have got considerably hotter, and these models were actually not self-consistent. So as a result, we kind of came to the conclusion that dusk obscuration was not a viable explanation to explain this dimming. So that leaves us with that fallback or failed supernova scenario being a very real possibility. But of course, the best way that we can really test this is to get a further image of 19 KRL, and that is what we plan to do. So we are going to observe 19 KRL with HSD in the upcoming cycle. And then we also have observations of GTC coming up as well. So that should really allow us to confirm or refute this failed supernova hypothesis, I guess. And so I'm running out of time, so I'll just leave my summary up. Thank you.
All right, questions for our final speaker?
That's a very interesting hypothesis there. It's a fallback and you formed the black hole. You've obviously got it survived, there's got a companion there because you've got, you can see something there afterwards, right? So you've got a binary. Is there an X-ray source there now?
I haven't looked at it in the X-ray, so I'm not sure, but maybe that's something that I could definitely look into. Thank you.
Anyone else?
Thanks for the very nice talk, Beth. Have you considered maybe that there was some like reverse shock that could destroy the dust, or that it's newly formed dust that then gets destroyed? I don't know if this is something. Are there infrared observations that can help with disentangling the possibility that maybe it did become dust enshrouded, either with new dust forming? We see this in novae, for example, when they go off, you can have, or actually somebody already showed Thailanda's a nice plot of 1309 SCO. So you do see dimming and then it comes back up again.
Yeah, we will be looking at in the near infrared as well for this. And as well as that, I think originally when I did this analysis, there was no JWST images of 19 KRL, but I have been told that there's possibly images that we might need to look into. I'm not sure about that, but I'm going to have a look and see in the infrared as well.
All right, let's thank Beth again. Are we going to have any flash talks? No. So in that case, let's thank everyone who spoke in this session. And after this, we have the poster session, and there are some posters from people in this in this focus meeting in there. So be sure to check them out, and we'll be back in half an hour.
Yes, and since we're skipping this tiny slot of poster flash talk, let's do it on the next session. I think everyone can present the flash talk there. There's enough time. Thank you.
Whereas, you know, naturally you would expect it to get redder.
Yes, that's why I was asking about
it
infrared.
yeah, it doesn't really get redder in the optical. You can get it like just the right kind of dust, just the right kind of temperature,
But it might produce some weird dust. I mean, it's a really interesting thought.
I mean, I just if it genuinely well, yeah, this is the thing. If you start out to metals down the dust out of it, right? So let's say this is an LED base thing. I know obviously the car is surrounded by dust. You kind of mix out all metals and dust out. You have to get it pretty quickly. And I don't know if you can do that without all the metals in the core. There's a lot of them.
I mean, so my reference point for these kinds of things is novae.
Yeah.
Novae do it. Some
Yeah.
only 40%, but some
Yeah.
do it, and we don't know why some do it and why some don't.
Flashbacks go in order, so there's one now and one at the same time tomorrow.
No, I recognize your voice.
Or when is the second?
Yeah, no, I think so. So the novae just they do it.
Yeah.
Now, and they do it quite fast also, but we don't understand
Yeah.
why.
No, it could be just the JWST stuff that Beth mentioned. So it's nearing. So it's probably like
So now you're also skipping, so it's going to be now after the
and
next
also the
session,
spatial resolution is gonna
all of the flash talks.
we
I
were
was
looking
also
at
really interested in the sodium
Yeah.
line because there's the slide
should
work
be around.
2006
Yeah. So that was
so again
yeah.
the nova connection
Yeah.
is type 1A.
So that was basically the idea we had. It's like, oh yeah. NASA did it for 1 year. We should.
Yes, exactly.
So the
Okay,
problem
so
is
it's
we're doing the
yeah,
low resolution
the session that
spectrum.
comes now.
So it's not as good. Instead, it has an ISO TOO program at the moment to get high resolution spectra at a couple of epochs of a 2N. But I need something really bright. I need something like 16 times UVEX. Because one again, you know, like sorry, about
Also, you mentioned mergers.
Yeah.
Reliable source for these luminous
Yeah.
Right. You showed an example for like the nice example you showed of a merger that we actually see the binary of a star. It's a low mass.
Yeah.
But But does it result in sort of magnitude?
So the ones that we would see, you know, they would have to be like a 15 and a 20 solar mass.
Okay,
Like
so
that.
they're higher mass analogs.
Higher mass analogs.
Okay, so these kind of
I'm
objects
Shelley
would
Chang from
not
Harvard.
pop.
No,
Yeah.
Okay.
Yeah, nice to meet you. You're from the University of Turku in Finland. Okay. Do people care about stars then? Do people care about stars in Finland? No one cares about stars in America.
No way.
I do stellar evolution.
Because you
And there's
mentioned
only like
mergers
3
are-
people like
Well, sorry, there's
in
one
America.
means
So like, you know, Lars Bilston, Matteo Contiello, Tim Fuller. I've worked with all them. And I'm working with Charlie Quinn right now. Yeah. So I'm trying to find stars. Charlie does not work on stars. To me, he works on galaxies. So he works on solar clusters.
How do you scale up the
Supernova.
energy? Because
You like the dying
like
star.
this peak energy.
I like the living
what's
ones.
the origin of
It's
it?
orbital energy.
Like the orbital energy.
Yeah, this is the conference for the bridging of the
A
gap.
bigger binary should give you a bigger binary.
All right.
And obviously
Let's
it's
go to
more
Smith.
like, I mean, I guess nobody knows how these things work, right? So if the different phases of it, it's not clear what's powering, say, the blue phase at early times, shock interactions, recombination,
Right.
storing, stuff like that.
Exactly. That's why I was wondering if there's simple scaling from low mass to high mass.
I mean,
I'm
it's
actually.
simple at the level of height. Can we think go?
Does it work with Itacar? Itacar, I don't know. You didn't mention it explicitly,
Yeah.
but you know that it has.
Yeah.
Problem. I mean,
Yeah.
the
Yeah, I
consensus
think,
I feel is
yeah,
that it's a
fine.
merge.
Yeah.
A merge. I mean, I don't really
Yeah.
believe that, but that's pretty common at least
Yeah,
in
I-
massive star fields.
Yeah, I would.
It's right now a binary,
yeah,
but
yeah.
the idea is that it used to be a
triple.
triple.
Yeah.
Yeah.
No, I'm reasonably comfortable with that.
So does that work?
Yeah.
For example, the scaling. I guess there's
So
some reason.
there are scalings for these mergers in terms of like say the progenitor mass. Some of we have progenitor mass estimates for. There are scalings then how luminous they are is what we actually observe is slope is different. So we know those scalings don't exactly work.
Right.
It leads them to the same direction.
Okay,
More
yeah.
massive is brighter.
That makes
but
sense.
They should have slope like this and
Yeah.
correlation
Yeah.
like that.
So you mentioned that mergers are common, but the cool thing about mergers is that they also pull things from the lower mass end, which are much more
Yeah,
common, right?
yeah.
I mean, okay, in your case, you need two massive stars to merge.
Yeah.
But generally, I think about this often, and I don't know if anyone has done this in detail. It's a bit outside of what you were discussing, but like, I don't know, even standard 2P
Yeah.
supernovae, red supergiants, which we think are kind of like
Yeah.
standard and boring. It makes sense that many of them are merger products
Yeah.
because they are being.
But that's, I think, John Eldridge had in one of the BPAS papers, or
Mm.
one of the top 10 papers, made this point, like, you extend the age with stuff. So if you say.
You extend
there's
the
no-
age and
yeah,
you get more
yeah,
stuff.
You've no way.
You can get, I don't know, a 4+4
Yeah, you can't,
binary,
you can't,
which
you
are much
can't
more
have
common.
someone like in a 100 megyear population, you can't have someone exploding as a 2P.
Right.
Unless you
Mm.
have like, you know.
Are there examples for that?
For individual objects, no, because I guess you don't have the ages of the population. But I think people have said, done like, you know, populations and, you know, all that kind of stuff. It's samples.
Yes.
But yeah, I mean, I think for sure most of the, like, most massive stars, most of them are in binaries.
Yeah.
So most of the 2Ps we see, if we all fit with single star progenitor models, most of those are binary.
Yeah. Not
Now-
to mention the stripped ones.
Yeah,
The stripped
yeah.
ones are very obviously.
But I mean, I guess for the hydrogen rich ones, there's probably a companion there, but it's probably hot, so it's probably not contributing much to the optical flux that we.
I mean, if there was a very nearby companion, they would not become red supergiants to begin with.
Exactly.
They're either mergers or they have far away.
Yeah. So I mean, I can't remember who else. Somebody says like, you know, white binaries are the best single stars.
Yes,
there are.
we say that often in the binary community.
But yeah, I think there's got to be some of the progenitors, and I think some of the 2Bs, like 2011 DH and another one, 93D. There's detection of the like just like a tiny little bit of blue X.
Yes. No, but it's the mergers that I'm actually most intrigued by. Anyway.
Yeah,
cool
no,
talk.
great talking to you. Yeah.
And happy?
Yeah.
Yeah.
Yeah. It's a very nice session. Very nice.
Good. Did you stay much longer yesterday?
Not so much.
No. What did I miss except as astronomer trying to that?
Okay. Okay.
Am I still turn the next one? Yeah. How do you do the online questions?
Will I monitor Zoom?
Yeah. Okay. Are you monitoring the Zoom or? Okay. Cool. So I guess you'll stick your hand up if there's a question online.
Yeah, it's a good idea to ask Zoom to
Yeah,
monitor this
okay.
question from time to time. Yeah, I'm monitoring, but so far no online question.
Yeah.
Cool. So then probably we'll be starting. So
Yeah.
this
He's
is gonna be a longish talk.
Yeah. Okay.
23 minutes.
Right. Okay. Including questions.
Yes.
So it's another 19 plus 4.
Yeah.
Thing.
So,
Okay.
yeah. Yeah, it's online now.
Okay.
It's a reply.
Yeah.
Hi, Dan. Okay. Yeah.
Hi, Dan. Hey. Okay, so I just did a quick attempt to screen share. I didn't have any problems. It'll be okay.
All right, yeah, we saw your slide, so it should work fine. So Morgan will be chairing your session.
Great.
Okay. Okay. We still have like 19 minutes.
Yep, okay.
Right. Thank you. Thanks so much for showing up.
No problem. Thanks for allowing this.
Of course, yeah. See you later.
Okay.
Okay. We're just about ready for the final session of the day. And our first speaker is Dan Purley, who's going to be joining us online, hopefully.
Yeah, thanks, Morgan. Can you see my screen and see me here and hear me? Didn't hear any feedback. Is that a yes, I hope?
Yep, we can hear you now.
Okay, excellent. So I'll begin then. So thanks for the opportunity to speak here. Sorry that I can't be there in person, but I'm going to be telling you about the fast side of the transient universe, which is an area that's produced quite a number of unexpected discoveries and surprises, and that will be the theme of my talk. So before I begin, I just want to thank some of my key collaborators, and in particular, Anna Ho at Cornell, who started as a graduate student at Caltech that I worked with remotely for many years. Who has really been the one that's been responsible for the majority of these discoveries, thanks to her work with developing algorithms to find things in optical data, as I'll describe to you later in the talk. Okay, so here is a version of a plot that I assume you've probably already seen many times today and elsewhere in this topic, which is a timescale luminosity diagram, sort of the most fundamental observational diagram of transient astronomy. So on the x-axis, we have the characteristic timescale, which can be defined various ways. It's how long it takes a transient to brighten and fade. And on the y-axis, we have the peak luminosity of the transient. And until about the turn of the century, there was only a relatively limited set of phenomena that we knew, and they occupied only limited regions of this diagram. But over the subsequent years from then till now, the development of better surveys that go deeper, cover wider areas, and at higher cadence have allowed us to sort of fill in many of the regions of this diagram that were formerly relatively unexplored. So these surveys here at right, as well as others, and others that are being commissioned now, have helped to find many additional phenomena. So you've heard about some of them already. For example, superluminous supernovae, rare but very luminous explosions. Intermediate luminosity explosions, sometimes called ILRTs or luminous red novae. You've heard about those as well. But also things over here on the left side of the diagram, which have durations that are shorter than those of typical supernovae, but still longer than the very, very fast GRB afterglows that were found and triggered by gamma ray satellites. And so that's going to be the subject of my talk. And there's two different types of things in this space, which I'll try to cover in the time allotted. And this region is interesting for a number of reasons, but I think if you wanted to come up with one single reason why we think of this space as a little bit special compared to others, is that there's a physical justification for why you need a very different sort of power source than you do in the rest of the diagram. In particular, to have something that is both very, very fast and very, very luminous, the radioactive decay power from the production of unstable elements in a supernova doesn't work, because to explain the high luminosities, you need high nickel masses. And if those nickel masses become comparable to or exceed the ejecta masses, then that doesn't really work as an explanation. And the ejecta masses are constrained by the time scale, because if you have too much ejecta, the transient slows down. So luminous and fast means you need some other sort of power source, and that power source is likely some sort of shock. And in particular, if the luminosity is high to begin with, to begin in this region of the diagram, the shock must be quite energetic. So there's two regimes in which we can have a shock that we can think about. The shock can either be optically thin due to some sort of relativistic synchrotron emission, and then we sometimes refer to that as an afterglow, or it can be optically thick and basically thermal, which can arise from a variety of phenomena, but the most interesting one is sometimes referred to as an F-bot, or a fast blue optical transient. So I'll describe each of these in turn, starting with the topic of afterglows and why we think these new surveys are perhaps providing new insight into how they form and what the population of these things out there is. Okay, so let me remind those of you in the audience who are not already familiar with the details of gamma ray bursts, what the basic model for a GRB looks like. So we have some sort of engine, probably a black hole, although it could possibly also be a magnetar, that is formed either due to the merger of a compact object binary, or in most cases, observationally, the collapse of a massive star. So that engine is somehow able to produce a relativistic jet. The relativistic escapes the star, travels into the interstellar medium, collisions of material within the jet traveling at different velocities lead to very energetic shocks. Those shocks produce high energy gamma rays, as well as longer wavelength radiation, but the peak is in the high energy gamma rays, and that's referred to as the prompt emission. And then that material begins to sweep up the surrounding interstellar medium or the stellar wind and slow down. And as it does, it produces a forward shock into the interstellar medium. And that shock, with its strong magnetic fields and fast-moving particles, results in an afterglow, a synchrotron afterglow of electromagnetic radiation across the EM spectrum, all the way from the high energy gamma rays down to radio wavelengths. And so there are many thousands of gamma ray bursts known, many hundreds of afterglows known. They've been studied in great detail since they were found to be cosmological, and the first redshift was measured in the 90s. And they have somewhat of an interesting range of properties. So when you correct for beaming, because we think these things are strongly jetted, strongly beamed, the energy is characteristically something like 10 to the 51 ergs. However, to produce the energetic gamma rays, you need a very, very high Lorentz factor. And to obtain a high Lorentz factor with a limited energy supply, 10 to the 51 ergs is a lot of energy, but it's not infinite energy, you can only accelerate a small amount of mass. So these jets are quite clean. They have only something like 1/1,000,000th of solar mass of material within them. And the beaming angles are relatively small, say a few degrees or so. And one thing that you might wonder about is that these masses and Lorentz factors in particular are really at an extreme of the transient phenomena we know about. When we think about supernovae or we think about other types of outflows, you rarely encounter numbers this high. You usually have for the Lorentz factor or this low for the ejecta mass. Typically, you have higher ejector masses and lower Lorentz factors. And so you wonder why there is such a wide gap between GRB jets with these super high Lorentz factors and super low ejecta masses and more characteristic types of explosive outflows from massive stars and other phenomena in the universe. And you might wonder, could that gap actually be filled in by some sort of phenomenon that we haven't discovered yet? Because the way in which we select GRB afterglows is very different from the way that we select other types of transients. They're seen in the gamma rays and then followed up at other wavelengths after the gamma rays have been localized. But if a jet did occur and it had a Lorentz factor that was sufficiently low, because of a variety of reasons, less Doppler boosting, and in particular pair production cutoff in the high energy spectrum due to electron-positron production, you actually would get few or no gamma rays. And so there could be a whole population of intermediate Lorentz factor events, say 5 to 10 to 20, maybe up to 30, which could be out there, could be comparably energetic, but just not be producing gamma rays, and therefore we're not able to find those afterglows if they exist. And that's sometimes called a dirty fireball. Now, if there are dirty fireballs out there, how would we know about them? Well, you have to do two things. One, you have to be able to find these things without gamma rays. And second, you have to be able to identify what it is. And perhaps the most important clue about what it is the rise time. So the rise time of the afterglow, the time that it takes to go from explosion to the peak luminosity in these longer electromagnetic wavelengths like X-ray or optical, more or less goes as T to the gamma to the -8/3, largely due to time of flight Doppler reasoning. And so for a very high Lorentz factor outflow like we see in GRBs, that time scale is characteristically only a few seconds. And in the few cases where we have observed gamma rays, our optical emission from gamma ray bursts throughout the prompt and early afterglow phase, that's typically what we see. But if the Lorentz factor was significantly lower, it would become quite a bit slower. So 2 hours for a Lorentz factor of 30 and half a day for a Lorentz factor of 10 to 15. So if we had a method of identifying luminous and fast, but not as fast as a gamma ray burst phenomenon in the optical or perhaps the X-rays, we might be able to find these things if they're out there. And so that has been the focus of many of us in the transient community. This Wiki Transient facility in particular has been responsible for most of these discoveries via a pipeline that my collaborator Anna Ho produced, although others have been contributing to a few of them as well. And so far, we actually have a pretty significant discovery list of afterglows that have been found. So far in optical survey operations through ZTF and a couple of other surveys, there are now 22 afterglows that have been detected in the general operations. So not because the survey was stopped to follow up an afterglow just happened to appear in the field of view during the regular operation of the survey. Of those 22 afterglows, actually most of them do have an accompanying GRB. And in some of those cases, the afterglow was only discovered because somebody checked out the GRB arrow circle and noticed an afterglow was there, but a significant number were found rapidly and blindly without needing to know that the GRB happened, and even in some cases before the GRB was announced. So that's already a clue about the frequency of this phenomenon, but I'll come back to that later. In 10 of the 22 cases, though, there was no identifiable GRB at all. So we checked Fermi, we checked Swift, we checked CONUS, and then there was no evidence of a GRB that could be detected coincident with the time and location of that afterglow that was found. And of those, we were able to get redshifts of 6 of them. Okay, so what is the characteristics of this population? Could they be dirty fireballs, or are they just the same population of things that we knew about already from gamma ray burst follow-up? Well, by and large, it's difficult to distinguish most of the events in the population from afterglows that happen to be coming from gamma ray bursts that just were a little bit too faint in the gamma rays to be detected by the current fleet of satellites. So what I show here is on the x-axis, the UV rest frame luminosity, which more or less corresponds to what we observe in the optical. And on the y-axis, the gamma ray burst isotropic equivalent energy. And in black, I show the population of Swift GRBs, and in general, things with more luminous prompt emission have more luminous afterglows as well. What we're interested in finding is things with very luminous afterglows and with very underluminous gamma rays with limits on the gamma rays. And what you can see here is that of most of the things that we've detected in ZTF so far, which we're able to get a redshift of at least, the limits, first of all, many of them are simply detected in the GRBs. And when we don't detect them, generally the limits don't rule out the whole optical population. There's one exception, but even that exception, for reasons I'll get to in a moment, doesn't suggest that it's anything that dramatically different from what we see in the ordinary GRP population. So for example, this event has a fast rise time. Okay, so to plot the rise time specifically, here I have, again, the peak optical absolute magnitude, actually peak UV absolute magnitude really on the y-axis, and the rise time on the x-axis. Remember that the rise time is an indicator of the Lorentz factor, at least in possible. There's other ways to slow down the rise, but a low Lorentz factor is one method by which you'll definitely get a slow rise of the afterglow. In black, I show GRB follow-up from the Swift era, and in red and blue, I show the ZTF afterglows. So as in the last plot, the blue ones are the ones with GRBs, and the red ones are the ones that don't have any known GRB. And so in general, it's very difficult to measure this rise time because typically we have a non-detection, a bright detection, and then after that first initial discovery, it's already fading. So it's very hard to maintain the kind of cadence that you need to find these things on the timescales over which a typical afterglow or even a slow afterglow would rise. But sometimes we can place limits. And usually those limits aren't particularly constraining, but we do have a couple of cases illustrated here in which there is a suggestion of a rise time that is significantly slower than we see in the typical GRB population. And this could, at least in principle, be an indicator of a lower Lorentz factor than we see in the ordinary GRB population. So I'll briefly go over the 3 of these because we're analyzing each of them in a lot of detail. So the first one that we found was in 2019. And in this one, we actually got quite lucky, not just to find it in the first place, which was a little bit serendipitous because our pipelines hadn't completely been developed yet, but also because TESS, the exoplanet satellite, happened to be looking at the same field at the same time. And that allowed us to actually resolve the rise, not with great signal to noise, but at least to show with reasonable confidence that it was pretty slow. So even though we don't have ZTF data that gives a strong limit on the rise time, the TESS data allows us to establish that it's something like 2 hours or so, which is about what you'd expect from a moderate Lorentz factor outflow of about 30. And that's also consistent with what we get when we model the afterglow in general between the optical X-ray follow-up and radio follow-up. On the other hand, we also can't rule out that this is simply a GRB with a core that's a standard classical Lorentz factor of several hundred, and we just happen to be observing it a little bit off axis, where the on axis to us outflow was slower, which would produce a very similar signature. Okay, so we have a paper on arXiv reporting on our results of that one. Now, another candidate, which is arguably an even better one, is this one, AT 2021 LFA, which we also discovered in ZTF, and also serendipitously was being observed by another wide area survey, the MASTER survey. And this one also shows clear evidence of a slow rise of about 3 hours, which, given the luminosity and other properties of this burst, points towards an even lower Lorentz factor of perhaps 10 or so, depending on exactly what you assume about the interstellar median properties and so on. And so far, we're still working on this event, but it is actually more difficult to model this event as an off-axis jet. So stay tuned for the details, but we're going to have a paper coming out hopefully in the next few months on this one. And you can also see the master paper, which comes to very consistent conclusions that's already out there. Okay, and then so getting back to the topic of surprises that I put in the title of this event, we also found one other curious thing that we thought initially was an afterglow, and in many ways, you could argue that it was an afterglow. It was consistent with synchrotron, and it had a very slow rise by GRB standards, although a fast one by every other luminous transient standard. It looked like the rise time was about a day. We detected it, and then we detected it again much brighter the following night, and then it immediately started fading. And we thought this was going to be another one of these orphan afterglows, perhaps a very good dirty fireball candidate. But then something curious happened, which is that it bottomed out and plateaued in the optical, and actually it started to become very luminous in the UV, and even more luminous in the X-rays. In fact, more luminous than any GRB that has ever been seen, comparable only to a very rare population of tidal disruption events that produced relativistic jets. And so something of an unexpected discovery as a result of this is that these afterglow searches are also finding what could be described as afterglows, but not coming from neutron star mergers, not coming from massive stars, actually coming from the tidal disruption of stars by supermassive black holes at distant parts of the universe. And interestingly enough, we found a second example of this just a couple of months ago that we're actively following up right now. Okay, so there's lots of indications that dirty fireballs could exist. We're still trying to model the data to make sure that they really do exist and they can't be interpreted in some other way. But I think what we can say a little bit more securely is that if they do exist, they can't be very common because we're not finding anywhere near as many as some of the optimistic theories had predicted that we would in surveys like this. So given the fact that about half of the afterglows that we discover in the opticglow have GRB emission already, and that we can't see all of the GRB luminosity function at the redshifts that we find them, and so many of the ones that we don't have GRB emission probably do have GRB emission that was just missed. And given the rates of the things that we find across the sky, what we can say right now is the all-sky rate of afterglows at detectable magnitudes, so in a magnitude-limited sense, compared to the known rate of afterglows from things like extrapolating the Swift BAT GRB rate, is not a large factor. So it's consistent with one, which is to say the Swift afterglows are all that exists. We can't even rule that out. And it's no more than a few times that, the true afterglow rate across the entire sky. So we can't say yet what these afterglows could be, but if these extra afterglows that could exist are dirty fireballs, they can't be more than a few times the GRB rate. And as surveys continue, unless we find a very clear example of a dirty fireball, or ideally more than one, this upper limit number is going to come down. And this is consistent with some other types of searches that have used different methods and inferred similar things. There just aren't that many examples of afterglow-like phenomena other than the ones that we know about from GRBs. They're not particularly common. And that might be telling us something interesting about what you actually need to form an energetic jet. Okay, so now before I move on to the next part of the talk, I do want to say that the prospects for kind of solving this in a more robust way are pretty good, because while the optical is a good way to find these afterglows, the X-rays are even better. And we thankfully have a couple of new X-ray missions flying now at soft X-ray wavelengths, which aren't affected by the issues which make low Lorentz factor explosions difficult to detect in the gamma rays. And these are both putting out detections of bursts at a steady clip, and perhaps some of them will end up being dirty fireballs. And if they don't, that will tell us pretty definitively that these things really truly are rare, or perhaps don't even exist. Okay, so moving on to the next phase of the talk, the fast blue optical transients, a much more mysterious class of phenomenon. So again, getting back to the timescale luminosity diagram here. So this is this kind of vague population down here with characteristic timescales of roughly days and peak absolute magnitudes comparable to a supernova, or at least that was the original definition. So the establishment of this class as something a little bit different from what we'd seen before goes back in particular to Maria Drout's paper using pan-stars in 2014, although there were a number of other papers around the same time that either reported on individual events or smaller samples from other papers with consistent characteristics. And so these events were notable because, unlike supernovae, they were very fast, but nevertheless the same luminosity as a supernova. And in the small number of cases where spectra were obtained, they did not show any significant features at peak. So it wasn't completely clear what they were. It suggested that at least the most luminous ones had to be shock powered for the same nickel mass, ejecta mass reason that I mentioned at the beginning of this talk, but it wasn't quite clear what they are and what their real origin was. So what really kind of blew the field open was this spectacular event, AT 2018 COW, which I'm sure many of you in the audience remember quite well if you work on this field, because it was one of these fast blue optical transients. It came up very fast, discovered by the Atlas survey by Prentice et al. And it was very, very luminous and very, very bright. And so we could just immediately start getting tons and tons of data on it from very early times. And virtually everything we saw about it surprised us. So it basically never developed supernova features. It only showed some narrow lines of hydrogen and helium. It had extremely luminous radio and millimeter observations, which were self-absorbed out to quite late phases, which we rarely see in any kind of transient for that duration of time. It had extremely luminous X-rays approaching that of GRBs. The X-rays were highly variable, going up and down by factors of 10 on a timescale of only about a day, shown here from a paper by Anna Ho. And so this already points to a number of interesting properties. The fast variability for most of us pointed towards some sort of central engine with a short variability time. The luminous self-absorbed radio pointed towards a lot of material around the burst, around the source prior to explosion. And the lack of any supernova features said it couldn't have actually produced very much radioactive elements at all and might be something quite distinct from a supernova. Okay, so what could it actually be then? Well, most of the models out there to explain this central engine and this rapid X-ray variability and the high shock inferred luminosities, energies in general, involve some sort of black hole rapidly accreting a lot of material from some sort of dying star, and probably in a very anisotropic way. So some examples of this would be a tidal disruption event involving an intermediate mass black hole, a supernova coming from a supernova-like phenomenon coming from a very massive star, but did not explode successfully, and so essentially just collapsed down to a black hole and formed some jets, a merger between a Wolf-Rayet star and a black hole. But it's really hard to be sure from the constraints that we have right now, because this was just one example. We didn't necessarily observe it optimally, and it's hard to know what attributes of it are real and which are characteristic and which were just sort of peculiar to this one individual event. So ideally, we wanted to find more of them. And so that has also been a quest of the last few years. We had already developed methods with CTF to find afterglows, which could pretty easily be adapted to finding other fast things in the same parameter space. But in this case, blue things instead of red things, and not quite as luminous as the things we were looking for in GRB afterglows. So one thing that we found right away is that there are different types of things in this general fast blue optical space, and most of them are quite different from 18 COW and not quite as unique or interesting. So I show here from a paper by Anna again, a few years ago, all the things that could be described as fast and luminous within this sort of canonical less than 13-day characteristic time and supernova-ish luminosities. And most of them, if you follow them up for long enough and get spectroscopy at later times, they actually emerge to be times of things that we know about. So at the low luminosity end, they're almost all type 2b supernovae, or in some cases 1b supernovae, but they have an early shock breakout from an inflated envelope. We know this is common in 2b supernovae, and their nickel production is less than normal, and so the second rise that we often see in 2b's isn't really there or isn't really clearly distinct. So you just see that initial shock cooling flash, and that looks like a fast transient, but this is very different from what we see in 2018 COW. And nothing anything entirely new. The next population of things that we see, the next most common population of things that we see in this space is type 1BNs, and more rarely the related phenomenon of type 1CN supernovae. So this is also a class of supernova that's quite rare, but has been known about for a while. They're definitely interaction driven. They have narrow lines. In many ways, they do have a number of properties that are common with things like 2018 COW, but they don't have the bright radio, they don't have the X-rays, they don't really have evidence of any sort of central engine. And again, because they've been known about for a while, they're not really necessarily the same phenomenon, although there could be some sort of relation. So it's only a small minority of things that really do have this set of extreme properties like 2018 CAO, the featureless spectra, the luminous multi-wavelength emission, and the lack of a supernova. But there are other examples, and we have quite a significant sample of them now, and we are learning things from the diversity of this population at this point. So here's the whole list of things that we have found. I think with one exception, all of these have been found with ZTF, this Wiki Transient Facility. For fun, we are trying to name them after animals, although this is getting harder and harder as time goes on and we start seeing letters like this in the alphabet, but we're trying. Each time we find one in the optical, we get follow-up spectroscopy, we get radio, we get X-rays. And in almost all cases, and essentially all cases, when we see things at 18, 2018 CAO-like luminosities and timescales, we do see those X-rays, we do see the radio. So we're quite convinced that this is a population. But the challenge with most of these is that they're all found much further. And so we can't get quite as good the same kind of really excellent data that we did with the CAO itself, which was at only 60 megaparsecs. Nevertheless, we are learning things. So let me overview just some of the brief properties of what we're learning. So one is at the host galaxies. So the CAO was in sort of an unassuming spiral host galaxy, low mass spiral in the nearby universe. And that's pretty characteristic of the population in general. They're in star-forming galaxies. They're rarely, perhaps never, in the most massive galaxies, but they're not necessarily in the lowest mass galaxies either. And all cases that we know of so far are in star-forming galaxies. So the story is not that dissimilar to what we see in GRB host galaxies, for instance. They're in star-forming galaxies, probably prefer the middle poor ones. Okay, host environments. Where do they actually happen in the galaxies? Well, a clue we knew right away from 2018 CAO was that it is not in the center of the galaxy. So here is 2018 CAO's host from a recent paper. There's a nucleus there. It came here from some sort of minor star-forming region in a spiral arm. So evidence that it suggested was some sort of recently formed massive star. However, it's not in the most massive cluster. So here's a bright cluster of very, very young massive stars. It's not coming from that. It's coming from the somewhat older, less assuming cluster here. I'll get back to the environment properties in a moment, but for now, let me continue to say about a few other properties of these things. So they all rise very fast. They all fade very fast, some not quite as fast as others. There is some diversity there, and they all stay, that we know of so far, stay very blue hot and hot on the decline and don't show supernova features. X-ray properties are very diverse. The CAO itself, of course, famously showed this rapid variability going out to late times. It's hard to see that kind of variability for these more distant events because of the limited number of photons that we get, but in at least some cases, there is evidence of rapid variability. And some of them can actually be quite a bit more luminous than the CAO itself. So the CAO, if anything, was kind of a weak example of this class. Most of them that we find are actually a bit stronger. So there is probably a very, very strong, rapidly variable engine in most of them. Radio properties. So again, the CAO was kind of is perhaps actually the lowest luminosity thing in the radio that we found. Typically, they have even more energetic emission. It's almost always self-absorbed or nearly so at early times. And they all show this sort of cutoff at about 100 days, after which the flux dies rapidly, which suggests that the CSM that we infer from the shocks has some sort of outer edge. And once the shock reaches that edge, the thing just kind of fades away. Okay. So those are sort of the things that are consistent with what we saw in the CAO, but we've also seen some surprises. So getting back to the theme of this talk of surprises, one of the big surprises comes from the UV. So that same UV follow-up that was initially got just to characterize the host galaxy turned out to discover a very hot, very luminous, too luminous to be a star, but significantly less luminous than the initial transient itself, persistent source at the location of the transient, with remarkable properties: 100,000 Kelvin, about 10 times the solar radius, and 10 million solar luminosity. So the thing had left some sort of very hot source behind in the optical, and probably also the X-rays, which I won't say much about because I believe you're going to hear about this in the next talk.
2 minutes.
Yep, thanks, almost done. But there is evidence that there's a very, very luminous source emitting all the way from the optical to the X-rays. That doesn't make a whole lot of sense if this is a massive star that's collapsed. You just need a lot of material that is just persistent for years after the explosion and still accreting, still producing energy. Okay, and then perhaps the biggest surprise of the past few years in this phenomenon relates to this event, 2022 TSD, which we nicknamed Tasmanian Devil. This didn't actually initially start out as one of our most exciting, best sampled, best observed events. It rose, it faded. We had a lot of gaps in our observing light curves. We had that sort of weird point up here in the ZTF photometry that we didn't initially believe. It looked like a cosmic ray or something. But eventually we got some late time follow-up with Magellan. And we saw something very surprising in the 5 exposure sequence. So this is 100 days after the explosion. And you can see here in a span of just 15 minutes, the source is actually appearing and disappearing on timescales of a few minutes. And so something was still there and still varying rapidly, even in the optical. And this is something we've never seen before. So here again is that 5 exposure sequence. It's going from 23rd magnitude up to 21st and then back down again. So it's going from nothing to a supernova like luminosity and then back down to nothing in just a few minutes. So we got lots of other follow-up. So this is from the Thai National Telescope using a high-speed camera, showing lots of variability on timescales as short as we can resolve them of seconds, again, reaching supernova-like luminosities here. So very remarkable source. And we saw many other flares over the course of that campaign before they eventually stopped about a few months later. So remarkable properties, variable timescales of a minute. The durations of the whole flare episodes are 5 to 30 minutes, reaching supernova-like luminosities, 10 to the 47 ergs. They have a non-thermal spectrum, so they're probably synchrotron radiation or something similar coming from the central engine that we're seeing very directly. Duty cycle is about 2%, and it lasted for about 4 months before we stopped being able to detect them in our late time follow-up. And there's no evidence of any periodicity. We've also never seen this in any other event. So if we wanted to represent the light curve, we have the overall thermal transient coming down, and then these synchrotron flares coming up out to a couple of 100 days. Okay, so I won't speculate on that right now. I'll leave that for the discussion, but this tells us lots of interesting things about what these events could be. So let me just wrap up by saying a little bit about the future. So just as there's new surveys coming up that we think will help us with finding dirty fireballs, there's lots of surveys coming up that will help us find F-bots. So in particular, these things tend to peak in the UV, and there's 2 new UV missions that are coming soon, Ultrasat in a couple of years and UVEX hopefully a couple of years after that. Which are both going to be conducting sensitive UV surveys of the transient universe. These are bright millimeter transients, which will be found very well with millimeter observatories. And if these flares, if they are a common thing, or even if they're not a particularly common thing, but they exist elsewhere, will be found by some of these wide area, super fast cadence things like the Argus array. Okay, so I'll end with my summary and take questions. Thanks a lot.
Thanks, Dan. Any questions?
Hi, thank you for the great talk. Do you have any radio data on in the first part of your talk, the tidal disruption event, AT, 2022 or whatever it was called? I only saw the UV and optical and X-ray. Do you have radio data on that?
Yeah, so I probably should have made a backup slide with the radio since I didn't include that to save some time. Yeah, we have a lot of radio follow-up of that one, and so in our paper by Igor Adrioni et al., who wrote that discovery up, we have the initial 60 days or so of the radio follow-up, and it basically is self-absorbed all the way to the millimeter as well. So that is also something that is propagating into a very dense environment. And the luminosity just goes up and up and up over the first few days. So it's indicative of a very energetic, not particularly high Lorentz factor, not particularly narrowly beamed jet that probably remained on for a long period of time. So that can be measured quite well in the radio. There have been a couple of follow-up papers since then as well, reporting on additional radio follow-up. But yes, that event and the previous relativistic TDE, which was actually found by Swift, both are very, very radioluminous.
Thanks.
We have a question online. Sumu, do you want to unmute?
Yeah, hello. Can you hear me?
Yep.
Yeah. So yeah, thank you for the nice talk. So unless I missed, regarding the luminous fast blue optical transients, what is their rate and how do they compare with those of supernovae and GRBs?
Okay, so the rate is it's not extremely well constrained because it is difficult to find things in this space and because they're very rare to begin with, but it's very low. So I think we have a rough estimate in one of Anna's papers. It's something like 0.1, even 0.01% of the overall core collapse supernova rate of the truly 2018 cow-like phenomenon with all the multi-wavelength properties and the highest luminosities and fastest rises. So which is much lower than some of the early papers said, because these early papers also included these 2Bs and the 1BNs and the 1CNs. So if you exclude those and you require the multi-wavelength emission and the featureless spectra and the cow-like properties, it's of order 1 in 1,000, maybe even less of the core collapse supernova rate.
Okay, thank you very much.
One last request.
So hi Dan. I'm interested in hearing more about the speculation about that late flaring. I mean, it's clearly accretion into the central engine, but I guess that you have strong limits for other events like the cow or whatever. So what conclusions do you have this time about that?
Yeah, so to speculate a little bit about this, what this might be, yeah. So it's hard to avoid incretion. So we see erratic flaring from magnetars, and so we know it's possible to get these from magnetic phenomenon. But the time scales and the energy scales and the fact that this thing literally just exploded recently before, and so many of the other characteristics suggest a black hole, do lead us towards some sort of accretion type of interpretation. So probably it's some sort of jet that is being produced and is quite narrowly beamed as a result of continued fallback accretion from the last bits of the star, if it's a star or that collapsed, or even if it's a star that merged with a massive black hole, something like that. And so it's producing these things along a narrow axis. We haven't seen this from any other event, and that might be a beaming phenomenon. So this just happens, TSD happened to be the one that we're seeing on axis. And in all the other FBOTs that we know to date, they're off axis. And so the flares are pointed in some other direction, so we don't see them. Yeah, so, but exactly what is causing them, why are they so extreme and energetic? I don't think we've ever seen this type of phenomenon from any other type of accreting system at these luminosities, at these wavelengths, et cetera. So I think there's quite a bit to be worked out there in terms of how you can generate this, but I think that's kind of the picture that the data points towards for now.
Okay, we move on to the next talk. So let's thank Dan again. And we remain working in the field of the cow. So Julia Migliori is up next.
Okay, good afternoon, everybody. I'd like to thank the organizer to giving me the opportunity to talk here. And I'd like to start acknowledging all the collaborators that helped contributed to the work that I'm gonna present. So given the excellent introduction, I will just skip the properties of luminous fast blue optical transient and take over from where we have been left, discussing the latest observation on 2018 cow, which can be considered the prototypical object in this category, and was luckily the target of a multi-wavelength coverage, multi-wavelength campaign. And in particular, in this talk, I'm gonna focus on the X-ray observations. So on top of what was already said, I'd like to add the fact that at early times, the source was displaying a complex X-ray spectrum with a hard X-ray hard power law, with a hard power law, and superimposed on that a Compton-Hamp like feature. In addition, between 6 and 7 kV, we also observe a complex spectral line that were interpreted as broadened, blue-shifted iron K-alpha line. Then, as it was said, there was also a rapid variability on hour to day with the hour to day flares. And then after 24 days, more or less, there was also a break and a sharper decay. So we follow up later on with XMM, the source, The idea was to characterize the behavior at late time, since these first observations were pointing at a compact object activity. The other point was also that, of course, if the X-rays are related to the central engine, we wanted to understand if it's possible to better constrain the properties of the source. Here you can see the evolution in time from the first period within 1 month, within 3 months. And then these are the last two observations that we got, 220 days after the third one, and then almost 4 years after the latest one, the fourth one. Despite it dimmed significantly, we still got a detection in both observations. The detection in the third observation was also reported in a previous paper by Yao and collaborators. So going to see the luminosity, what we see is that if we compare with the previous evolution, in observation 3, the flux has significantly decreased, but it's more or less in line with the decay that we observe after the break after 24 days. However, if we look at the spectral, at the X-ray spectrum, we see that the emission has significantly softened, going from 1.6 to more than to about 2.9 as a photon index. We should say that given the limited statistic, the spectrum could be also modeled with a multicolor black body with a 0.2 keV temperature, and the model are more or less indistinguishable statistically. Then when we go to the last observation, we see that the source has further dimmed. However, it diverged completely from the previous decay. This could be interpreted in two possible ways. Either we are observing a sort of plateauing phase, if the observation is truly related to 2018 cow. However, this level of luminosities are also compatible with the X-ray luminosities that we expect in the case of star formation processes related to the host galaxy. So at this stage, it is difficult to discriminate between the two possibilities. And although there are also indications that the source is still active in UV and optical, as we have heard, we cannot fully exclude that the last observation is dominated by X-ray emission from star formation. So putting our observation in the context of the broadband spectrum, concerning observation 3, we see that, as was previously observed, radio that were also performed at the same time of the X-rays and X-ray emission clearly are due to different components. However, the X-ray detection can be modeled in the framework of disk models together with the ultraviolet emission that was detected and was discussed in the previous talk. The parameters for the disk are consistent with those that have been inferred from the UV works. However, what we see in observation 3 is that on top of the disk predicted X-ray emission, we observe also an excess which could be related to the fact that we are still observing the hard component visible at early times. Then moving quickly also to the last observation, we see little evolution in terms of modeling of the disk, and this is true even if we consider this as simply as a upper limit. The disk model that we applied was either a standard Shakura-Tsunaev disk, and under this assumption, what we obtain is that the mass of the accretor is in the range of what is expected for intermediate black hole masses. Compatible in terms of scenario with the intermediate black hole mass tidal disruption event. However, if we relax the hypothesis of a thin disk, then also smaller masses in this range and compatible with the QPO detection constraint are also possible. What is interesting with this hypothesis is that at that point, the source must have gone in at early times, must have undergone a super Eddington accretion phase. This is in line also with the model that was proposed, one of the models that was proposed, that of a Wolf-Rayet black hole merger scenario. And in addition, the super Eddington accretion phase could also explain the formation of this broadened and blue shifted iron K alpha line. So going to my conclusion, what we could do following up 2018 at late times was to derive constraints on the mass of the accretors, which suggest the fact, which point to the possibility that this kind of phenomena may be super Eddington accretion laboratories, and even though rare, makes them particularly appealing also to study the physics of black holes under extreme condition. Of course, we need more sources and better sampling, both at as we can see in this plot, at early and at late times. And thank you very much.
Thank you. Questions?
Thank you very much. This might be a naive question from an outsider, but I was wondering, why do you need the merger scenario in there? So if you currently still have a UV source and it would accrete on a black hole, couldn't it just be that the black hole was freshly formed in a failed supernova and now you're accreting from the remaining star that you would maybe even see in the UV?
Okay, first of all, I'm also an outsider. I come from AGN community, so it's okay. So this was one of the other possibilities. If I well remember, one of the possibility that was favoring the merger scenario was also that there are constraints related to the density of the medium that were inferred from optical, and which probably were better explained in the context of a binary system where the binary has lost previously part of the mass. But I mean, this is one of the possibility of the scenarios that we have considered, but at this time is not, I think, exclusively defined, of course.
We have one question on line one, if it's a very quick question. You can unmute yourself. Okay, I guess maybe.
Okay, maybe on Slack.
Yeah, you can ask the question on Slack. So let's thank Julia again. And our next speaker is Koki Uno, who is talking, continuing on rapidly evolving.
Okay. Hi everyone, I'm Koki Uno, a PhD student from Kyoto University. So today I'll talk about this F-bot light curve modeling. So we focus on the optical properties of F-bots. So yes. So first I introduced the rapid evolving transient observation. So in 2000, supernova or nova-like very long time scale transient has been discovered. But thanks to new generation surveys like GTF or imposters, so from 2010, rapidly evolving transients like which time scale is around several days are discovered. So these transients provides new insight for stellar evolution, and we are surprising that much more diversity than expected in rapidly evolving transient universe. So we one of the most interesting and enigmatic transient is fast blue optical transients we called F-bots. So F-bots shows very high luminosity. So the orange and green one is a typical type 2P and 1A supernovae. But compared to supernovae, the peak luminosity is 100 times brighter than these normal supernovae and shows very short time scale evolutions. So the most famous object of F-bot is 2018 curve. So curve shows very high luminosity. It reaches 10 to 44 L per second and shows power law decaying light curves. And the ejecta velocity in the initial phase exceeds 0.1 light speed. And from early phase, the photosphere is decreasing, but the temperature is constant. So we compare the supernovae and 18 curves properties. So compared to supernovae, the photometric properties are completely different from supernovae. So we, especially the photospheric radius evolution is very interesting because in normal supernovae, if we assume the homologous expansion, the photometric radius is increasing and the temperature is decreasing. On the other hand, the super 18 curve shows decreasing photosphere and constant temperature. So the properties cannot explain by homologous expansion like supernovae. So we need to consider how to explain the decreased radius with constant temperature. So we are motivated by how to explain the characteristic features of 18 curve. So here we suggest that we propose that continuous mass ejection like outflow can explain these peculiar properties. And we propose a wind-driven model. This is analytical light curve modeling of F-bots or like this supernova-like very fast transient. So this is a concept of wind-driven model. So the key point is this model is powered, assumes that continuous outflow determines the density structures and temperature structures. So for example, so this is the innermost radius and branches the outflow, and the outflow is characterized by outflow rate and velocity. So in the initial phase, outflow front is the same position as the photospheric radius. So, but after that, the outflow becomes transparent and the photosphere decreasing goes inwards. So the photosphere radius is decreasing, but this is a steady state like solution. So the temperature keep constant. And after that, this model close to the steady state solutions. And this model is characterized by the mass outflow rate and velocity and the innermost radius. In this is a schematic picture of the wind-driven model. So for example, the innermost radius is equipartition radius is between the thermal energy and kinetic energy. So this is equipartition radius. And the outflow is launched from this radius, and initial phase, this is very optically thick, so the temperature determines the adiabatic cooling. But after that, the density decreasing, the temperature structure is determines diffusion cooling, and this picture can determine the density structures and temperature structures, and we can define typical radius of like photon trapping radius or color radius. This is photospheric radius. So using this model, I try to explain the F-bot interesting optical properties. So first, to simplify the model, I neglect the time-dependent term. This is I apply the steady-state model, so neglecting the time-dependent term. Model applies each snapshot of the observational snapshot and try to explain the curve evolutions. So the model suggests that the peak outflow rate is around 20 solar mass per year. So this is too high to explain the single star evolution or single star activity. So this high massless rate indicates that common envelope or some black hole related systems are driven by drive the curve properties. And interestingly, we does not assume the time dependent index, but our fitting results suggest that the m dot, so massless outflow rate, depends on the time dependency with the power law index of -5/3. So this is the typical time evolution of accretion systems. And so this high massless rate and time dependency suggests that the central engine of the curve is a black hole system or black hole accretion systems. So we speculate that the central engine is TDE or failed supernovae or something. And after that, I consider the time dependent model. So this is a light curve fitting of the 18 curve. So the peak magnitude is roughly consistent, and the time dependency, temperature dependency is roughly consistent. So this shows constant color evolutions. So the early phase correspond to this phase, and after that the model this result this phase correspond to the time steady state like phase. Okay, so this is the physical properties derived from the fitting results. So eruptive mass ejection reaches to the 20 solar mass per year, and outflow rate index is -5/3. And so we skipped this radius, but the outflow branching radius is 10 to 13 centimeters, and the total mass ejected mass. So this value is derived from the integration of the massless rate, and the total mass is 0.2 solar mass, and the total kinetic energy is 10 to 52. So these physical range is correspond to the failed supernova activity or tidal disruption events. So if we assume these central engines, the parameter is more reasonable in this our scenario. So this is a summary of my presentation. So my talk is based on these 3 papers, so please see it. Thank you very much.
Thank you. Okay, we have time for some questions. Oh, Dan.
Yeah, thanks. Great talk. So you say it's consistent with both the failed supernova and the TDE model. Does your model have any predictions that could be used to distinguish the two? Since what we really want to know ultimately is to confidently say it's one or the other. So is there any observation we can get to help?
Two scenario is a bit difficult because we only assume the kinematics of the like this. So I cannot mention about the central engine, but the curve has the offset from the central region of the galaxy. So we suspect that so failed supernova scenario is much better, or so like TDE by IMBH seems to be good, but it is difficult to distinguish that these two scenarios only based on our scenarios.
Okay, thank you.
Do we have any more questions? Okay, if not, let's thank Koki again.
Thank you very much.
And next up is Nicole Lloyd-Running, who is, yeah, we're getting faster. We're talking about GRBs now.
Just checking the laser clicker. Okay, hi everyone. My name is Nicole. I'm a staff scientist at Los Alamos National Lab in the Computational Physics and Methods group. And I'd like to talk to you about a lot of things today related to GRBs. And I'm grateful that Dan gave his talk because he gave a bit of the intro. I still would like to orient us all on what a GRB is observationally. So how do we see GRBs? On the left-hand side, we have counts per second as a function of time in seconds. I apologize, the axis is not labeled on the bottom, the x-axis, but that's time in seconds. We see a burst of gamma rays, a highly variable burst of gamma rays in the hundreds of keV range. It can last anywhere from less than a second to hundreds or even thousands of seconds. So that's usually what we see first. And then that's followed by long-lived afterglow emission, which can last days to weeks to months to years. That shines across the electromagnetic spectrum, as we heard earlier. This is the most popular slide in all of GRB talks. Credits to NASA for this. So what's happening, as Dan mentioned earlier, we believe that prompt gamma ray emission is coming from internal dissipation processes in this relativistic jet. It can be internal shocks. You can get this also from magnetic reconnection events, any kind of internal dissipation there. The afterglow occurs when the front of the jet sweeps up enough gas to begin to create a shock and decelerate, and this creates this long-lived fading afterglow across the electromagnetic spectrum. There are two sort of classes of progenitor models. The first, this thing is not going to play, but I'll try. The first is for the prompt gamma ray emission that lasts less than around 2 seconds. We think that comes from the merger of two compact objects, like two neutron stars or a neutron star and a black hole. For the prompt emission, that gamma ray emission that lasts longer than 2 seconds, we think that is associated with the collapse of a massive star. The energetics and the timescales all align with those scenarios. Both of those progenitors create a central engine that launches a relativistic jet. A very viable one is a black hole accretion disk system, but you can also have models with a neutron star at that, in that central engine area. Okay. So this is our theoretical framework for how we understand GRBs. They are the most luminous objects in our universe, emitting 10 to the 52 ergs in a matter of seconds. We would love to understand every part of them, from the microphysics of let's go back. The microphysics of this internal dissipation, the black hole accretion disk system, what's happening in the hydrodynamic scales out with the external forward shock, to how we understand them in the context of the evolution of our universe. So they have the potential, because they are the most luminous objects in the universe, because those jets are at Lorentz factors on the order of 100, they probe physics that is of the most extreme in our universe. So the problem is, as I'm sure many of you can appreciate, is the length and time scales involved in modeling them across all of the scales we would like to understand them spans more than 20 orders of magnitude. So it's completely intractable in a single simulation. So my group at Los Alamos is developing approaches to sort of piecing together codes and scales to try to understand every aspect of the picture that I showed you. And we begin with modeling the progenitor itself. So we're focusing a little bit more on the longer ones, the prompt emission that lasts more than 2 seconds. So those GRBs that are associated with massive stellar collapse, but we do allow it to be in a binary system. Okay, so we model stellar evolution, including binary interaction with the open source code MESA. We'll evolve the star to the end of its life and try to feed those properties, its angular momentum, its stellar density profile, into the initial conditions of a general relativistic magnetohydrodynamics code, also open source, Athena++. That helps us understand the jet launch and power. We take particle and cell codes to model the jet itself, the relativistic plasma physics of that jet, and we have some exciting new algorithms that can take larger time steps than traditional algorithms in particle and cell codes, if you want to ask me about that later. Finally, if we have a viable progenitor that we think will create a GRB, then we ask how many of these are in our universe? How do they fit into our broader understanding of stellar evolution? And we model that with a population synthesis code called COSMIC. Okay. I'm not going to go through every one of these plots here. I'm just going to give you the bottom line. And this is some of the output from some of those simulations. But what I want to emphasize and what I hope you take away before I move on to the next part of what I'd love to talk with you about is that a massive star collapsing with a compact object companion that can influence it over the course of its lifetime makes a powerful, pun intended, GRB progenitor system. So that companion can spin up the star over its lifetime. It can also influence the environment around the star. And so just very, very quickly at the top, this is showing sort of how the star, the angular momentum is a function of time for the star with a companion at different orbital separations and how it's spun up. This is our GRMHD output, and the power in the jet, which well exceeds the power that we need observationally. And this is something from our population synthesis that is consistent with what we're seeing observationally for how many of these GRBs are in our universe. Okay, so that's lovely to understand a single system and how it works in the physics of the progenitor, the black hole disk system, the jet, the afterglow. But what I'm most excited about is because these things are so very bright, the most luminous objects in our universe, and because we can then see them to such high redshifts, how can we use them to understand star formation and stellar evolution in our early universe? So that's what I want to finish up my talk discussing, is how to use GRBs to estimate the high redshift star formation rate. Before we can do it, there's an annoying thing that we need to worry about, and that is that jet opening angle. Remember, we really only see those GRBs that are pointed right at us, so we miss a good fraction of them. The narrower the jet, the more we're going to miss. And it seems like there is an anti-correlation between jet opening angle and redshift. That is, there are jets at higher redshift, jets from GRBs at higher redshift appear narrower than those at low redshift. And this is really doing our best to account for all selection effects that might artificially create this. Why would that be? Just very, very briefly. Jet undergoes collimation as it punches through the stellar envelope when it's launched. That collimation then depends on the density of the stellar envelope. And let me give you just the bottom line here so I can get to my final slide. We think that stars in the early universe that are lower metallicity and more dense can collimate the jet better. So that's what's going on. When we account for that jet opening angle evolution. So let me slow down here. This is the star formation rate as a function of redshift. This dashed line is this typical Maddow-Dickinson 2014 star formation rate that we often see. And this green line is the star formation rate estimated from GRBs without accounting for the jet opening angle evolution. The magenta line shows the star formation rate from GRBs when we account for that jet opening angle evolution. And we can see that that produces, as expected, much more star formation, or we estimate much higher star formation in the early universe when we account for that. Now, what's going on here with this uptick at low redshifts, you can ask me about. We think that might be a contribution from another progenitor, even a compact object mergers. But let me leave you with my bottom line. Either way, whether you believe that jet opening angle correlation or not, there's more star formation at high redshifts, according to GRBs. And I can end that sentence there, but even more so when we account for that opening angle evolution. And I will end there. Thank you.
Thanks, Nicole. We have some questions. Dan again.
Hi. So, I mean, a number of us have looked into the use of GRBs at high redshift. And of course, there's a lot of evidence at low redshift that the GRB phenomenon is already very metal dependent. We don't see them in metal-rich galaxies. And so if you don't account for that, that has a significant impact on how you infer the star formation rate. And a lot of the differences go away if you try to model that out. So when you show these rates, have you tried to take into account metallicity evolution of the universe directly into it, in addition to this possible opening angle correction factor?
I mean, when we estimate, oh, let me get to the microphone. When we estimate that rate, we are taking just a kind of a direct, if I understand your question, you're asking, do I kind of estimate the fraction of stars that make GRB as a, metallicity dependent as a function of redshift and factor that in? Is that?
Yeah, because you have to normalize the curve because we don't know the exact offset. And so if you change the normalization factor at low redshift to adjust for the metallicity dependence, then it brings down the numbers at higher.
That's right, and we have done that to some extent, but there's too many examples of there's not a very definitive metallicity GRB correlation. There's a lot of theoretical arguments, and on average they're in low metallicity galaxies, but I can find you exceptions to that. So I'm a little cautious to go too heavily in making a correction factor that's very definitive, but we have done that. So yes, is the bottom line to your answer or your question.
Okay, thank you.
One more quick question. If not, let's thank Nicole again. And our last speaker of the session and the day is Michelle Zuidenhout, we're getting even faster now on FRBs.
Okay. Hi, everyone. I'm Tian. I'm a postdoc at the University of South Africa. And I'm going to tell you about how we find fast radio bursts with Meerkat. So just a quick summary of the status of the FRB field at the moment. FRBs are brief millisecond duration flashes of radio emission, and they're very energetic. We've seen them from about 10 millijansky up to about 150 jansky, which I think is about 10 to the 44 per second. And they originate from distant galaxies. So the ones that we've been able to localize to host galaxies, they come from redshifts, from various redshifts up to greater than 1. Most of them are one-off events, but a small subset of them, about 1 in 10, do repeat, but it's a non-periodic repetition. But we have seen some very long-term periodicity in the activity cycles of them. So some of them have periods of high activity and low activity, and that is periodic. For example, 121102 has I think 170 odd day periodicity or activity cycle. So that might be an indication that we're talking about a binary system here, or maybe that's an indication of precession or some other rotational effect. We've detected them at various different radio wavelengths from 110 megahertz to 8 gigahertz. There have been various searches for counterparts at different frequencies, but none successful, so they remain a radio phenomenon for now. And the progenitor channels are still very much uncertain. There are many models for what's causing them, typically involving some compact object. Magnetars are very popular at the moment. So I work on a survey called MeerTrap, which uses Meerkat to find these things. And the important thing about it is it's a commensal survey. So as other users use the telescope to gather their data, we have equipment that intercepts those data and then uses it in real time to look for these transients. And so we've been running continuously for about since the end of 2018. So we've amassed thousands of hours effectively on Sky in that time. In order to maximize our chances for finding FOBs or other transients, we we tile the primary beam of the telescope with these small tide array beams, 768 of them. And then each of these can be independently searched for transient signatures. So it's kind of a fly's eye view on the sky. And so the data from each of these little beams goes to a specialized compute cluster running a specialized search pipeline, which takes those data and spits out a list of possible transient candidates. And then we have a machine learning classifier specially built to distinguish possibly real transient candidates from interference. So we've been running for about 5.5 years now, more or less continuously. And in that time, we found about 60 new fast radio bursts. That works out to about 1 every month. And also about 100 galactic transients or pulsars, which is about 1.5 every month. So a central problem in FRB science at the moment is that of localization. The vast majority of FRBs that have been discovered have come from CHIME in Canada, which is a telescope with a huge field of view, but pretty terrible angular resolution. So of the 800 or so FRBs that we currently have in our sample, only about 50 of them have positions that are accurately enough known to pin them to a specific host galaxy. The benefit of doing this search with Meerkat is that because Meerkat's an interferometer, we can pretty much instantly localize the FRBs that we do find down to very high precision. And in order to do that, we employ a transient buffer system. So that means that we look for the transient in time domain data from the beamform data. And then once the pipeline gives a positive candidate, we go back to the imaging domain, to the baseband data, and save a chunk of the imaging data around the time of the candidate, and then use that to reform an image and to localize the transient, as you can see there, sorry, to sub-arc second precision. So about 1/3 of our FRBs have been localized well enough to do host galaxy association directly. But the transient buffer system that I just described only came online within last year, so that rate should increase significantly going forward. This is an example of some transient buffer localizations, 6 FRBs. These are from a paper from Inés Pastor Marizuela that should come out quite soon. So each panel here, there's a a white circle, which shows the location of the FRB. And it's an animation with each frame showing 1 millisecond of integration. And you should be able to see within each circle, there's a little flash. So once we've localized the FRBs, we work with the fast and fortunate FRB follow-up team, or F to the 4 for short. And they are a dedicated FRB follow-up project that do follow-up for FRBs discovered with various different telescopes. And they supplied us with these images from Gemini South and DESI, and we were able to associate our FRBs to within about 2 arcsecond precision with these host galaxies. Another important good thing about MeerKAT is that it's a very sensitive telescope. So this is a plot showing the excess dispersion measure against redshift for FRBs that have known host galaxies. The known population is shown by these black dots. And then the the MeerTrap sample are these ones with the blue diamonds. So you can immediately see we are finding FRBs up to higher dispersion measure, so further distances basically. And then we have a couple of FRBs for which we have dispersion measure values, but no redshift yet. So we are waiting for spectroscopic data to get redshift measurements for the host galaxies. And we have a few of them that are very high DM. You see this one up over 2,500 units. And so once we get redshifts for those, hopefully we are able to constrain this MACWAT relationship to much higher redshifts than has been possible before. Another thing we do with our FRBs is to look for persistent emission. So a few repeating FRBs, we've seen this diffuse emission, persistent emission. So that's not when the FRB is not bursting. And those observations are consistent with potentially being wind nebula from young magnetars. So we've searched for this similar persistent emission from our sample of FRBs. This is an example 2019-0714. It's localized about there. And the host galaxy from the Pan-STARRS survey is the white contours. And then this blob is from a MeerKAT observation. So we saw some diffuse emission, but because it's unresolved, we can't say whether it's associated with the FRB itself or maybe just a star forming region within the galaxy. But so we're doing more similar searches for more FRBs in our sample. We have one coming up for 15 more FRBs. And then just very finally, last result, we finally found our first repeating FRB in June of this year. And it happened to be a hyperactive repeater. So in a DDT observation of 2 hours, we found 95 bursts. You can see it has some nice spectrotemporal behavior. And we were overlaid it on a DESI optical image, and it's consistent with one of 2 possible host galaxies. So we are currently working on getting some better images to hopefully associate with one of those 2 galaxies. And I'll just leave my conclusions up for you to read, and I'm happy to take some questions.
Thanks, Tim. So questions? Yep. Well, thanks for that. Really, so I'm part of the craft team using ASCAP to localize FRBs.
Yeah.
So you're starting to see them really pushing the to high DMs, but I wonder if you've been perhaps a little bit optimistic with your potential richer ranges there.
Yeah.
Especially the repeaters seem to show potentially very high excess dispersion measures, and it gets high redshift as more and more foreground objects that could contribute to that DM. And then of course there's that really nasty local host dispersion measure contributions. So I think you might find a few of these, if you can get redshift for the host at all, you might find them somewhat lower than the ranges that you've applied there.
Yeah, no, I was definitely being optimistic for the sake of a nice plot. But yeah, very likely once we do get the redshift, we don't really expect it to lie in that range. But either way, it's going to be very constraining to the relation and very useful. Yeah, yeah, exactly. Yeah.
Okay, do we have any last? Yeah, Antonio? Online again. Susumu, do you want to unmute yourself?
Yeah, hello. So I couldn't hear the previous question very well, but it may be quite related. So you had a plot of the redshift versus dispersion measure of the mirror trap FRBs, and it seemed like the values, especially at high redshift, they seem to be quite a bit biased toward the higher and compared to the cosmic mean, expected cosmic mean. So is this indicating that the contribution of the host dispersion measures might be quite a bit larger than what was indicated by, for example, the ASCAP results?
Sorry. Yeah. So yeah, you can see that our FRBs going up to the high redshifts, they are above the trend that you get from the McWatt relationship. And I think probably most of that is attributable to the difficulty of disentangling the interstellar medium's contribution to host galaxy contributions. Yeah, it's difficult to say once we get redshifts for those at the high redshift or at the high DN ones. Will they be in those ranges or won't they? It's still up in the air for me.
Okay.
Yeah, okay. Thank you very much.
So we've got to move on to the flash talks now, but before we do, let's thank Tian and indeed all the speakers again. And it does flash talks.
All right, so now we're getting to the flash talk session. So the first up, when you see the slide, just go ahead to the podium and deliver your talk. And if you know you're next, then get ready. It won't take long. Please go ahead.
Okay, I had something before this. It was a PPT. So there was something before this. So it was like one slide with different. No.
It was converted to PDF.
Okay. Okay. So yeah. So I will jump ship here. Like I work on massive binary evolution. So what I want to talk about is if you have like, if you think of Wolf-Rayet stars, then you would think it's hot and helium burning. But what I want to show today is that you can have Wolf-Rayet stars also on the main sequence. So where's the laser? Yeah. So this is a donor star. So before the interaction, you have like a O star spectrum, but after the thermal timescale mass transfer, you remove a lot of mass from the star. So the L over M rises and it can show emission lines. So, and what the next plot shows is that if you compare the optical depth parameter of this model, which is shown in this black line here. So before the mass transfer, the optical depth parameter is much lower. Then after the mass transfer, it rises a lot. And then you have this stripped donor phase where the optical depth parameter is in the right ballpark as observed Wolf-Rayet stars on the main sequence. Now, this is interesting because these stars, since they are on the main sequence, you need the least number of assumptions to model these things. And we also have a lot of observations. So my poster is about studying the observable properties of a population of these Wolf-Rayet-like stars on the main sequence. And we also have follow-up ESO UV's multi-epoch spectra coming up for 3 of these systems where we will try to derive empirical constraints on the strip toner phase in massive binary evolution at the high mass end. Thank you.
Hi everyone, I'm Patrick Joroge Mwaniki from Kenya at Meru University of Science and Technology, and I'm an MSc student in physics, specializing. I'm an MSc student in physics, specializing in astrophysics, and my MSc thesis is on meerkat-based modeling and study of supernova remnant under the supervision of James Chibueze and James Chibueze from University of South Africa and Dismas from Meru University of Science and Technology. So my study, this is the airbird image on meerkat, which is beam size with a beam size of 5.71 arcseconds, and this is the radio structure of the meerkat with the very prominent blowouts. One is the south, and another one in the west, and another one in the east, with the faint one dominating the northwestern part. So this one is the spectral index map, which is synchrotron radiation with a negative spectral index map, showing that this source is a synchrotron radio source. And to compare with other wavelengths like optical and X-ray, which is in cyan, we combine the observation in meerkat and the XMM observation in the X-ray, which is in the contours, cyan contours, and the optical region, which is the most important for this source, is in and a contour image depicting the two filament A and filament B. This divide gives the modeling nature of the supernova remnant G7.7. And this is the title of my poster. Thank you.
Thank you.
Hi, everyone. I'm David Kaltenbrunner, and I'm a third-year PhD student at MPE in Munich, Germany. And what I'm presenting on my poster is our soon-to-be published paper on the population of high-mass X-ray binaries in the Large Magellanic Cloud that we detected with eROSITA. And there's two major things inside of the paper. The first one is that we did very detailed multi-wavelength analysis of each individual object in the catalog. And then the second is that we did a study of the entire sample. For example, here we see the luminosity function of our sources, which is closely correlated or connected to the star formation history. And also what's really new about this is that it's the first catalog of high-mass X-ray binaries in the entire LMC, because the outer regions out here have never been studied in X-rays before. Yeah, unfortunately, my poster was in the previous session, so if you're interested in the topic, just come to me and talk to me. Thanks.
Thank you. The poster is always available on the conference page. Yes.
Hi everybody, I'm Fabrizio Bocchino, Observatory of Palermo, Italy, and I'm presenting an optical monitoring campaign with very short cadence of a selected sample of galactic red supergiant. Why we are doing this optical monitoring campaign? Because we are seeing that we have more and more interacting supernovae, in particular the one that showed ionization flash. And for a few cases, after ionization flash, we have a type 2P, 2L supernovas. That means that also low mass red supergiant may undergo very intense mass loss episodes at very late stage of their life. And if we were able to detect this, in principle, we could determine the evolutionary stage of the supergiant, because there are a few works in the literature that show that these pre-supernova outbursts may be related to late stage core burning phase of the stars. So hopefully we could determine these outbursts and study the star and time the exact evolutionary stage of these stars. Thank you very much.
Okay, hi. So I'm Tuomas Kangas from the University of Turku. And this is an ad for my poster about this weird stripped envelope supernova 2023 AEW, which is going to be visible tomorrow morning, actually. So come check it out. And also check out this paper, which is on arXiv and will soon be on ANA. So this supernova basically originally was thought pretty uninteresting. It was classified as a type 2b around here, which is already weeks after peak. So people just kind of stopped following it up until it started dramatically re-brightening here. At the same time, the spectrum, which was originally a type 2b, turned into a 1c. I'm not going to go into any kind of detail here. So for that, you need to check out the paper. But or come talk to me tomorrow, of course. But I will just say that it might look like this is an eruption followed by a supernova, but we don't think it is. We think this is the supernova, and this is an internal power source that for some reason turns on or becomes visible only several months after the explosion. Thank you.
Then I think she has to travel this time, so she's unable to give the flash talk. So let's move to the next one.
Hello, my name is Niko Pyykkinen. I'm also from University of Turku, and this is the ad for my poster, which is about a case study of this type 1b supernova. And so here you can see there you can see a light curve of a relatively normal type 1b. It's the one just below the red dots. And this supernova has this extended light curve with much more luminosity later on. And it's also very interesting that it has no hydrogen in no hydrogen in its spectrum. So it's because it's clearly an interacting supernova. So it's interacting with an hydrogen for CSM, which probably it has helium. So I think that this could be a star that was in process of losing its helium layer when it exploded. And that could give us some clues about how helium stripping actually happens in the stripped envelope supernova progenitors. Yeah, you can come see my poster. It's also tomorrow morning. So if you have any questions, you can ask them there. Thank you.
Hi everyone, I'm Kostas Antoniadis. I'm working at the National Observatory of Athens, and I'm a third-year PhD student. So my work is about the mass loss rates of red supergiants, and let's begin with mass loss, why it's significant, because it can affect the stellar evolution and finally the fate of the star and maybe the resulting type of the supernova. So we gathered the largest sample of red supergiants in different metallicities in different galaxies to examine also if metallicity affects the mass loss of red supergiants. And then modeling the SEDs of each red supergiants, we derive the mass loss rates. In the middle, in the middle, you can see the main results of the mass loss rates versus the luminosity. And you can see also this kink, which was also observed in a previous work by Yang et al. In the study of the SMC. And it's a new thing which shows an enhancement of mass loss. And we also compare our results with different works, and we discuss where the discrepancy comes from, because you can see that they can differ by orders of magnitude. And also that the kink we saw here, that it's also related with the variability. Finally, the last plot shows the result with all galaxies together. And we can say that we don't find a strong correlation with metallicity, although further investigation is needed. For more, come and talk to me. Thank you.
Angela Zaccarelli is online, I think.
Yes, hi everyone. I hope you can hear and see me well.
We can hear
Okay.
you.
Okay, perfect. So, hi everyone. I'm Angela Zaccarelli, a postdoc at the Ruhr University in Bochum, Germany. And my poster basically summarizes a recent work that I made with some collaborators regarding core collapse supernovae from red supergiants and blue supergiant stars. These kind of progenitors, our hypothesis is that these kind of progenitors can host some relativistic jets that are launched by the central engine, and these jets can be choked within their very extended hydrogen envelope. So in this case, because there is the missing of a gamma ray counterpart, we have investigated the possibility to detect in the coming years also other electromagnetic signals, for example, UV and optical, thanks to the advent of new facilities, for example, the Ultrasat satellite that was mentioned in one of the in the first talk of this session. So basically, in our work, we have found a way to optimize proper follow-up strategy among UV optical and also high energy neutrino telescopes, under the hypothesis that this system can also produce high energy neutrinos because of photodronic and photomeson interactions. So basically, we have studied, our work is located within this context, and we have defined a proper follow-up strategy to try to figure out the existence of choke jets in this kind of progenitors and core collapse supernovae. If you are interested about results and details, you can come to talk to me tomorrow afternoon. If you're interested, you can also have a look at my poster and scan the archive of the first version of the paper that we submitted to NDA. So thanks a lot, everyone.
Hi, everyone. I'm Cristina Turner. I'm living in Spain currently. And I want to show you this beautiful multi-wavelength picture and analysis of one of the closest gamma ray burst host galaxies we have to date, a very nice spiral galaxy. In the middle, you see the composition of everything ranging from UV to, so UV, of course, the blue. Red is ALMA CO emission, and the white cloud is H1 from VLA, which you also see on the other side. We did a lot of studies on that. We also have amazing Muse data. So we have a Muse cube of the entire galaxy. So we could do a lot of analysis of the star formation rate, metallicities, and see if the GRB region is any special. And so the GRB was located in the outskirts of the galaxy, which we sort of expect because spiral galaxies usually have, sort of inside-out star formation. The star formation is going on not too much in the center, but in the spiral arms, as you can see. And also the outskirts are expected to be more metal poor because did it just fail? No. Because we think that GRB progenitors have to be metal poor. But you see that the GRB region is not especially metal poor. It's not something, I think this is like half failing, half not. I don't know. Okay. And so we did a lot of analysis. There is, it has high star formation rate in the region of the GRB. As I said, lowish metallicity of nothing extraordinary. It has a young stellar population, one of the youngest in the host galaxy. And we then compared it also to some other samples of GRB sites. Unfortunately, the sample of that is really small still. It's less than 10, where we are able to resolve properties at the GRB site so far. And you see that, for example, in metallicity, well, in most of cases, it lies like somewhere around the average. The host mass is very high because it's an exceptional galaxy. The metallicity is rather high. On the other hand, the supernova that was accompanying this long GRB was rather faint. So there's something that we're going to investigate in the future, probably, maybe some connection between the luminosity of supernova and the metallicity. There could be something. We have detected a companion galaxy because we are curious about where does the star formation come from to produce such a massive star in a sort of average star forming spiral galaxy. There is a companion that we detected actually in H1 data at 183 kiloparsecs. That's pretty far away. They could have interacted in the past. It would have been interesting actually to see the H1 gas between these two galaxies. That would actually be something for the other session on H1 stuff, because they have been detecting a lot of amazing stuff in galaxy groups. And yeah, so we wanted to have a conclusion of why do we have a gamma ray burst in these seemingly ordinary galaxy. And by the way, spiral galaxies, although lower redshift universe are, I think, like 40–50% of galaxies are spiral galaxies. Only about 10% of GRB hosts a spiral galaxy, so they usually do not occur in spiral galaxies. And unfortunately, despite all the analysis that we've done, we don't have the answer for it. It is consistent with models, low metallicity, high star formation rate, but maybe there's something more to it. So if you want to know more, either see my poster tomorrow or go up on archive, the paper that's at the moment in press in astronomy and astrophysics. Thank you.
Thank you. This one, this is the last one. Is Willow here? No, online? No. Okay, so then that's probably all the speakers today. Let's thank everyone again for all the nice talks and posters. That's it for today. We meet again tomorrow, same place, same schedule, 10 o'clock, posters downstairs and talks from 10:30 here. Thank you, everyone.